Okay, good morning, everyone. So for those who don't know me, I'm Yan. I'm a physical oceanographer by training from Hong Kong. So today, I'll share some work over the past 4 to 5 years, focusing on eddy parameterization problems, but over very steep topography. So I have several collaborators listed here, which will also be identified along the way. Oops. Okay. So to motivate, this is a study by Gruber et al. 2011, about over 10 years ago, who are using a very high resolution physical and biogeochemical coupled model to show that along the eastern boundary upwelling system, when all of the nutrients are being pumped by effluent transport all the way to the coastal zone surface, they are simultaneously exported by mesoscale eddy transports. So this process is prominent across the entire eastern boundary upwelling system, so will be important for the marine productivity globally. So this is from biogeochemical perspective, and if we go to the polar region, so this is a subsurface temperature from the very high resolution LLC run. You can see a very strong Antarctic slope front, which is separating the warm water offshore from the cold water onshore. But embedded in this frontal structure, you can also see a lot of coherent structures representing the mesoscale turbulence, which are shown increasingly to export or import the warm water from offshore all the way to the ice shelves, which will impact the water mass transformation based on returning circulation, etc. So these are only 2 examples out of many showing localized regional eddy processes responsible for global responses here. So my research focus really highlighted by these shining belts on this global map topographic slope, most of which are actually concentrated across the continental margins, which is the interface between the coastal and open ocean regions. The representation of mesoscale eddies across these regions are really challenged by the fact that the ocean depths are varying from about 4 kilometers offshore all the way to the tens of meters in the coastal zone. So, for example, Stuart Thompson in 2016 were using a very idealized model of the entire slope front. So this is basically a radicity field along some neutral density surface. So if we go from the deep ocean all the way to the continental slope, then to the shelf, you can see that the spinning structures are increasingly smaller. So even if we have a global eddy permitting resolution model run, for example, could possibly resolve well all those coherent structures in the deep open ocean. But if you go to the shallow regions, it's very challenging to explicitly resolve all these eddy processes and transports. So the only question is how to parameterize them, even in a very high resolution ocean model. That's basically the focus here. So in nature, that basically, from our perspective, there are 2 types of continental frontal structures or frontal systems, exemplified by this idealized models. This is a pair of idealized models, which I'll be using throughout this work and serving as a major tool for testing of ideas. One is so-called, well, more like an upwelling system, but more formally is called retrograde frontal system, which we define as in which the isopignals, when it's tilted, in the same direction as the underlying topography. So both are tilted onshore here, upward here. The other is more like a downwelling system, or more formally called a prograde system, in which the isopignal is actually bending downward, intersecting sometimes with the topography and opposing the tilting direction as the one on the left. So there are also cases, for example, in the entire slope front, there are hybrid frontal system that's including both features, but it's always dominated by one of these features. So it looks like just from this very idealized models, they only differ in the asymmetry of the isopignal tilting, so the dynamics should be easy to analyze. but it's not. For example, this is a major contribution in this field by Paul XX in 2011, who are using a very similar pair of idealized model to quantify the eddy buoyancy diffusivity here in the y-axis. So that's a GM coefficient across both prograde and retrograde fund systems. So this as the x-axis here, this is normalized some topography slope. So in the middle, we have 0 topographic angle, which means it's a flat bottom region. Then it's, from this point, it's diverging to the both sides here. So all those red markers here are representing the diagnosed diffusivity and normalized across both frontal systems using a set of simulations here. Now, if you check the scattering patterns, this is a log scale. So scattering are pretty broad here. And also, if you check the trend here with topographic slope here, it's not monotonic. So it's very complex. Apart from that, there is very strong asymmetry between the prograde and retrograde fund systems here. You can see that one is decaying really fast or rising again when the topographic slope is steepened. But on the other side, it looks like it's more monotonic, so much more scattering here. And all those behaviors, they can't be captured by theoretical models from linear QG theory, for example. So a more practical strategy to, for example, to parameterize all those red markers here are really trying to separately treat these two systems. So one by one here. So if we look at the frontal system and prograde here, so for this very idealized channel model, we can really make long-term and some long-short averages of key flow quantities shown on the left here. So in the background color, we have this eddy kinetic energy distributed over a long term. So the eddies are most energetic across the continental slope here. And also, you can also see that in the same location, we have very strong baroclinic prograde jet here, represented by the solid contours. It's very baroclinic, very strong toward the surface, associated with this very tilting isopycnals in the same location here. So if you think about it, it looks natural, but if you think about it, we have most energetic eddies at this location, but they don't seem to be very efficient in driving the restratification here. Otherwise, we would not have this very strong tilting isopycnals. And also, if we think from the parameterization thought line, using some energy dependent scheme, then when the energy is really high, it should serve to restratify the ocean more efficiently. But somehow, we have the most energetic eddies, but the least efficient restratification here. So to understand this more from theoretical view, so I'm invoking the geometric theory by David Marshall about 12 years ago, who are showing that the eddy buoyancy diffusivity can actually be constructed as some coupling between the eddy energy on the right here. So if we go back, so energy is really high here, okay? It's coupled with some rescaled ED time by this parameter alpha here. So this alpha is like efficiency parameter, which is controlling, although you have amount of energy, but how much of this energy are useful to restratify the ocean here. Now we can go from this theoretical scaling, for example, to quantify how much energy can be extracted by eddies through the restratification from the background potential energy reservoir here. Now, in energy conserving system is identical to the growth rate of the nonlinear eddy energy written on the right. So this is a very simple expression, but it tells that if we cancel out all the energy on the right here, it's saying that, well, this parameter alpha here is basically dependent on the nonlinear eddy growth rate normalized by the ED growth rate here. But in an equilibrium system, it's not always straightforward to quantify the growth rate with nonlinear eddies. But still, we can borrow some wisdom from coastal oceanography, which has a lot of literature showing that, well, the nonlinear eddy growth rate in prograde function system is essentially constrained by a non-dimensional parameter, which is a Bog slope Berger number here. So if we combine these relationships, this is basically saying that, well, this alpha could be some analytic function of slope Berger number. If we test these ideas diagnostically in our eddy resolving model, so this is a scattering plot between the diagonal eddy efficiency parameter on the y-axis against the slope Berger number in the same model here. These are from a bunch of simulations, and all those orange markers here, they're basically taken from the continental slope regions underlying which you have the strongest topography. So you can see that as the topographic slope is getting stronger, corresponding to an increase in the slope Berger number, and also a decrease in the eddy efficiency, and also the scattering here, inclusive of both slope region and also relatively flat bottom region. They're pretty compact, which allows us to fit some analytical functions of this dependence of this alpha against the slope Berger number. Now, after this, we can actually insert this alpha back into the geometric theory to get a scaling for the eddy buoyancy diffusivity shown here. So again, this is from diagnostics. So in the y-axis, this is a theory. No, in the x-axis is theory, y-axis is the Diagnostics diffusivity. Across many simulations represented by different colors here, with different topographic width here, and also stratification, Earth rotation, and forcing. And also it's inclusive of 3 regions. All those field parts are really corresponding to the continental slope regions. They're pretty tight here. So again, this is a diagnostics. How do we convert this into an eddy closure? To achieve this, and basically invoking the subgrid eddy energy budget constructed a few years back by Julian Mack for realizing the prognostic testing of geometric theory. So in the subgrid, we have this, well, more or less conventional subgrid eddy energy budget, very similar to those implemented in MOM. Then it's coupled with eddy buoyancy diffusivity. So basically, if you have an eddy energy at each model timestamp, it will inform the strength of eddy diffusivity. Then this eddy diffusivity will feed back as a baroclining source. So they're mutually informing each other. But this time, we also introduce a new ingredient for which this alpha parameter is no longer a constant as before, but analytical function of the topographic slope represented by this topographic slope Berger number here. To test these ideas, we also coerced our channel model from about 1 to 2 kilometers, which fully eddy resolving, into over 25 kilometers. So basically, we're killing all the eddy processes by coercing the grid. And this grid size is exceeding the largest deformation radius offshore in the open ocean region here. So for comparison, we also tested a list of other existing GM schemes, some of which are constantly using Earth system models, including some optimized constant GM coefficient. This is a WSPEC 97, then 3 variants of the geometric scheme, but without considering the topographic slope influence. So in this figure, you see a lot of colors in the background. This is basically the difference or the biases of baroclining velocity if you compare the parameterized simulation against the eddy resolving simulation here, and also superpose the thermocline structures of isotherms. So all those black lines are from high resolution model, standing for the truth. Then this green dashed line basically taken from the parameterized solutions here. If we compare all the existing results against the proposed new scheme here, you can see basically the bias is overall much more reduced. And also, if you compare the matching of the thermocline structure between high resolution against parameterized simulation, the matching is getting way better here. To be more quantitative, We also quantifying the biases of baroclinic transport across the entire channel, and also the biases heat content in the lower panel here. So there are different bars corresponding to different colors represented by different GM schemes. Again, consistent with previous testing here. So for a single case, we just seen before, this purple one here corresponds to the scheme I'm selling here. So this is a new scheme. This you can see that basically, regardless of which metric we're taking, reducing the bias substantially compared to existing schemes. The same conclusion can be extended to other cases in which we perturb the topography, stratification, etc. here. So overall, the new scheme is given the lowest biases here. So that's basically the testing for the pro-grid frontal system is basically accomplished within 2 years, so very straightforward. But if we look at the other part, which is a retrograde frontal system, in which we have upwelling here, it's becoming notoriously difficult. So again, I'm showing some key quantities along short average and also over very long term after equilibrium on the right. So at this time, I want to show the momentum responses. In the background colors, the blue ones means that along-shore flow is into the page. If you compare the figure with the one on the left, it's consistent with the direction of the wind here. So that's understandable. We have a momentum source at the surface importing the same direction of momentum here. But if you look at the distribution, it's really strange. So apart from this retrograde current here, we also have this red color sitting above this topography. Those in more like intercurrent or counter-current system, whose direction are basically opposite to the wind direction here. Now, also superpose a lot of arrows here. So those arrows are representing the fluxes of along-shore momentum by mesoscale eddies. So the story here is this. If we have a wind that's very strong over the continental slope here, represented by this marker here, it's injecting a lot of momentum, but instead of transferring the momentum all the way to the sloping bottom downward, those momentum are first being transferred offshore in the lateral direction. Then when it's reaching some region that's not embedded with a very strong topography here, it's transferred downward for dissipation. As a consequence, the entire along-shore flow here in this simple system is being shifted offshore with surface current core represented by the second marker here. So there is a 100-kilometer offshore shifting here. And when this shifting is really strong, basically you get emergence of all those intercurrent structures here. So that's basically the story. This is not a single case reported in the literature. So in studies of the Western Arctic Boffa gyre here, for example, Gorgi, Manolis, and Polaric Saxon, they also construct some similar approaches, and by comparing simulation without or with a continental slope on the margin. So when you're including a more realistic topography on the margin here, they basically also found that the retrograde current is entirely shifted offshore, and also there's some emerging intercurrent over the continental slope here. Now, in the context of the polar oceanography, this entire response also corresponds to very different freshwater contents between the two cases. So this has some implication of the deep convection in the North Atlantic. In another case, very recently, so Andrew Stewart was constructing more complex model configurations here with rough topography and also adding some along-shore pressure gradient forcing to simulate the eastern boundary upwelling system in isopycnal model. Now, in this case, if you take some along isobas coordinate system, you can also basically get the same result here. We have a retrograde current that's shifted offshore, but intercurrent emerging over the shelf and slope here. So this is a cross section. This is a plan view here. Okay. So to capture this momentum responses, using this residual mean framework here. So we have the along-shore momentum on the left, which is determined by 3 factors on the right here. We have, of course, the external forcing that initially drive the flow, but also in the middle, we have this eddy form stress, which is responsible for transferring momentum downward in the open ocean region, corresponding to an eddy buoyancy flux across the slope. And also we have this eddy Reynolds stress, which is playing a leading order role over the sloping topography, responsible for driving the momentum export across the slope here. If we integrate this momentum equation vertically, if you're studying the Southern Ocean, we get a very familiar secondary circulation balance system. In the middle, we have this very classical ACC balance. So eddy restratification compensated by this Ackermann transport, but this time we're talking about continental slope region, Ricci-Griffon system, in which the eddy momentum flux serves as some jet shifter trying to shift the entire flow offshore in an adiabatic system. So this is saying that basically if you want to parameterize even in a simple system for the Ricci-Griffon, we need to parameterize 2 types of fluxes instead of just 1. So this is basically complicating everything, especially in prognosis simulations. I'll show later here. Now, to close for the eddy form stress or buoyancy flux across the slope, me and Stuart, a few years ago, we basically followed a similar approach as in the pro-Griffon system. For example, if we're invoking the geometric theory again, but basically constructing the eddy efficiency parameter here, not as a constant, but as some analytical function of topographic slope, except this time we're using the so-called slope parameter defined as a Buck ratio between the topographic slope against the isopycnal slope, entire water column here. Now, in the top panel, I'm just comparing the scaling of the eddy diffusivity before and after this topographic adaptation here. So if we only consider this eddy efficiency as some constant as in previous studies, basically you can capture the variation of eddy diffusivity either across the continental slope represented by this very dark markers here, but not in the open ocean or the other way around. So it's not simultaneously capturing both regions, but after the adaptation, we capture both regions here, as you can see from 2 different color scattering here. The same approach also applies actually to other existing schemes. For example, we also adapted the Rhine scale-based Mixlin scheme here, which is popularized by MOM6 studies. Again, instead of treating efficiency parameter as a non-dimensionalized constant, we constructing some analytical function of topographic slope, again, using a slope parameter here. Before and after this kind of adaptation here, just to emphasize in this very simple channel model, you can really define the Rhine scale using the topographic PV gradient. But even if you're doing so, you can't easily capture the very strong variation of eddy buoyancy diffusivity across continental slope by this darker markers here. So we have to add something more. So that's basically closures, well, theoretical closures for the eddy buoyancy fluxes. So what about eddy momentum flux across the slope? So we're basically constructing theoretical scaling again by noting that the momentum flux divergence across the slope, this is essentially the same quantitatively as same as barotropic vorticity flux across slope. So which can be quantified as a coupling between some eddy PV diffusivity in the barotropic sense with the barotropic PV gradient induced by topographic slope. So I'm neglecting the negative sign on both sides here. Then the PV diffusivity, we're proposing that is basically a linear function of eddy kinetic energy rescaled by this Earth rotation rate here. The cool thing about this scaling is if you make some rearrangement and making some scaling analysis, you get very straightforward and clean relationship. It's saying that, well, the momentum flux that's crossing the slope is basically linear dependent on the eddy kinetic energy here. This relation is mathematically exactly consistent with a geometric version by David Marshall, showing that the cross-term momentum here, well, you can see a very complex, it's essentially also a linear dependence on eddy energy. Then in a barotropic sense, the eddy energy itself can be rescaled as eddy kinetic energy. So that's from that point of view. We go to the turbulence community. This is also resembling the so-called selective decay principle of two-dimensional topographic turbulence. So basically in a system, barotropic turbulence, random topography, if you have very weak damping but finite turbulent energy, it's very easy to promote this coherent vertices to form. Now, this vertex is very small, but if you think about it from a vertex gas problem, it's a small structure inducing a far field flow that's very efficient, trying to homogenize a PV induced by the topography here. So, but does this scaling work? Are the same consistent with different perspectives? It turns out to be working pretty well. So this is a diagnostics of scattering between the momentum fluxes against eddy kinetic energy across a channel I'm just showing, across many different simulations with different configurations here. It's basically collapsing onto some straight line here. And also, Andrew Stewart also tested scaling in his more complex model of the Eastern boundary avalanche system. You also get a very, very clean relationship between the two quantities, actually. Now, we have the theory, we have to convert this into eddy closure, test this prognosis, but because we need to close for two types of eddy fluxes, so just as the first trial, instead of using a subgrid eddy energy budget, I'm using some very small neural networks. So we basically train very small artificial neural networks. So based on the eddy resolving model outputs, so inputting the mean and topographic quantities into that to learn the eddy kinetic energy, or learn both quantities, both from eddy kinetic energy or the momentum flux itself. Then after the training process, because a very small neural network can really write all the weights and biases into the source code, then at each model time step, it informs the eddy diffusivity and also the moment forcing. Of course, we're imposing some global constraint in a channel model to make sure that the eddies only redistribute momentum but not generating them. Then both processes will feed into the momentum equations and tracer equations of the MIT GCM source code. So to further simplify the analysis, we're also making a bunch of two-dimensionalized parameterized simulation in which we use only one grid point in the along-shore direction because eddies are three-dimensional processes will kill all the eddy processes explicitly. So any eddy effect must be parameterized. So these are some results before comparing the isopycnals here. Again, black are from the eddy resolving simulations. The red dashed lines are from the parameterized simulations. Okay. All the way from a constant GM scheme, Wisbeck, and the two state-of-the-art, but without considering topographic influence. And you can see, in any case, it's generating different errors. For the new scheme, this is the result. You can basically see that the matching is much better and much tight, no matter we're considering the open ocean region or the slope region here. Again, we can make this more quantitative. These are basically diagnosed bulk quantities from eddy resolving simulations for heat content and Berkeley transport across different simulations with different model configurations here, represented by these black dots. If we're superimposing the parameterized solutions, a constant Wisbeck, not so good, then I'm imposing all the variance of the schemes I'm testing. But now it's very messy. We don't see much. by removing all those that's generating large errors, that has been left as this pair of the bathymetry-aware forms of the geometric and Rhine scale-based schemes here. So these are some visual. So you may wonder, what if we just parameterize the GM, but not the momentum flux? So we get the flows like on the middle here. So we have very strong retrograde currents concentrated on the continental slope and no intercurrent. If you compare those solutions again with eddy resolving solutions here. And if we add it into the momentum flux parameterization, we get the intercurrent and also the overall shifting of the retrograde current system for both schemes. Now, for the last part of this talk, I'm going to do something that's not very consistent with machine learning spirit. So I'm going to abandon all those artificial neural networks because I want to do that physically. Again, invoking the subgrid eddy energy budget coupled with eddy diffusivity, mutually informing each other. But this time, we're also using the linear function of eddy energy to inform eddy momentum flux. Now, the existence of this eddy momentum flux is indicating that we also have barotropic source or sink energy in the subgrid here. It's interacting with alongshore mean flow. This is not backscatter because the net energy production is very much negligible. It's only redistributing momentum and shaping the entire flow here. Then it's fitting into the model tracer and momentum equations here. So for a two-dimensionalized system, we get OK system, we get intercurrent on the right and also some shifting of the retrograde current. We're not refining this further because the current version of geometry basically mainly imposing vertically invariant eddy forcing, so we know where to fix it. A more important question, what about coarse grid three-dimensional simulation? To get a feeling about this, so this is a model solution in a coarse grid solution retrograde found system with the same forcing, but no parameterization at all. So we don't have intercurrent, we have no overall shifting of the retrograde current system, but the stratification is okay because the isotherm structures are very resembling the high-resolution model simulations. So if we check the surface vorticity structure, although it's very coarsened at this resolution, exceeding the largest deformation, but still resolving the larger variabilities, indicating that, well, whatever is resolved, they are doing an okay job in setting up stratification, but not the momentum flux. So inspired by this observation, we're basically modifying the subgrid energy budget. We mute off this GM part because the resolve flow already doing that, but imposing the eddy momentum flux in the subgrid again. But this time we need some driver for the subgrid eddy energy. So instead of using GM, we're using some dissipated energy from the biharmonic, from the flow component deviating from the alongshore mean. So we ensure that it's a dissipation of variability feeding into the subgrid. And by doing this, we make some online isobus average per time step. Yeah. I'm closing. Yeah. Sorry about that. Okay. So the last two slides here. So again, this is a comparison of the parameterized simulation. We have intercurrent and also overall shifting of the retrograde current in the coarse grid after a spin-up time. Not perfect, but okay, because it's vertical invariant forcing. Also some comparison of the variability of surface flow. And if you check the background colors here, if we have no parameterization moment flux, all this variability embedded in the very strong sign change of background vorticity, but with the parameterization, we keep the variability and meanwhile very weak variability, or very weak background vorticity sign change here. So that's basically all I want to share, and thanks for your attention.
Thank you so much, really interesting. Let's keep the questions for the discussion part. And also, if you can go and talk to Jan at the break. Really cool stuff. Let's move on for the sake of time. So our next speaker is Houssam Yassin. He's here. So Houssam is from University of Colorado Boulder, and he'll be talking about re-energizing ocean mesoscale eddies, assessing backscatter parameterizations for global ocean models.
Hi, everyone. So my name is Houssam. I'm going to be talking about backscatter in quarter degree CSM 3 Mom 6. And so backscatter in one word is, a few words, is basically how you go from this simulation right here to this simulation right here, which is much more energetic. And I'll be talking about that. And this is work done with collaboration with people here, as well as the so Gökhan, Gustavo, Ian Grooms, and the wider Eddy Energy client process team. Okay, so yeah, so the main overarching question we're trying to answer here is how do we parameterize eddies in a quarter degree CSM MOM6, right? So in a 1 degree ocean model, you're not resolving eddies over most of the ocean, and so you're practically resolving eddies only in the light blue region right at the equator. And so you need to parameterize eddies, mesoscale eddies, almost everywhere in the ocean, and you do that with isopycnal height diffusion, so like the Jamet-McWilliams scheme, right? But in a quarter degree ocean model, you start resolving eddies over a portion of the globe, right? And so this is somewhere in the green region in this map. And so now you have a region where you're partially resolving mesoscale eddies and regions where you're not resolving eddies at all. And the question is, what do you do in this situation? Okay, so the first question you can ask is, do you even need to parameterize eddies in a quarter degree model? Maybe you already have enough eddies, right? And the answer to that is that you actually do need to parameterize eddies. So if you have a 1/10 of a degree model that's unparameterized, you can see how quickly it's heating up over time. Then you have a 1 degree parameterized model with the GM parameterization, and you can see you can tune the 1 degree model to heat up at the same rate as 1/10 of a degree model. But if you have a quarter degree model that's unparameterized, you can see it's heating up too quickly, right? And that tells you that that the eddies aren't doing everything they need to be doing in this model. So there aren't enough eddies, which act to cool the model. And so I guess so you need to parameterize mesoscale eddies somehow in a quarter degree model. And so the first thing you can say is like, what happens if we just apply isopycnal height diffusion? You turn on a GM scheme, and it turns out because it's a diffusion, it's going to basically smooth out your height surfaces, and you're going to get rid of all your bare clinic eddies, right? And that's not very desirable because you have this very expensive model you're running at high resolution, and you're killing off your eddies with the GM parameterization. So that's not ideal. And then the other problem you have in a quarter degree model is that you're partially resolving eddies over part of the globe, but these eddies are very close to the grid scale. So they're being excessively dissipated by the hyperviscosity, right? So over most of the globe, you have just 1 or 2 grid points per deformation radius, and your eddies could be missing as much as like half or even more of their energy. So modeling eddies in quarter degree model, you have 2 problems, just to summarize. If you need some eddy parameterization. If you apply isopycnal height diffusion, you're just going to eliminate the eddies you're resolving. And the eddies you are partially resolving either are just too dissipated by the hyperviscosity. And the solution we have here is just we're going to apply backscatter instead of isopycnal height diffusion, where we are partially resolving eddies. And so the way backscatter works is that in your momentum equation, you already have a hyperviscosity term that's dissipating energy at the grid scale. And what we do is we add an anti-viscosity term, right? And that returns energy to your flow. And because the anti-viscosity term is a Laplacian, which is less scale selective than the biharmonic hyperviscosity, the energy is being returned at slightly larger scales, which kind of mimics the inverse cascade in the ocean. And so our goal here is to basically, we have 2 goals. Our first goal is to test out backscatter in CSM, and our second goal is to actually compare various different backscatter schemes. So for this talk, I'm just going to be showing how backscatter works in CSM, and so we haven't gone to the comparison part. But we're not the first to apply backscatter in a global model. You have Urike et al. 2020 in FISLAM 2, and then you have Chang et al. 2023 in OM4 MOM6 at GFDL. And so what they've seen in their global model is that when you turn on backscatter, you have much more eddy energy in your models, and you find that backscatter reduces SST biases in the northern hemisphere. So you see that there's long-standing Gulf Stream SST bias, and you turn on backscatter, it projects really favorably on that. And then there are like many different backscatter schemes, and they differ in how you choose your anti-viscosity coefficient. And all I want to say here is that, the scheme we're applying here is similar to the one applied at GFDL in Chang'e 2023, except that our one has a vertical structure. It's not barotropic. The one they applied was barotropic. Our one has a vertical structure, but otherwise it's very similar. Okay, and just to go through the basics of the model setup we're using. So we're testing backscatter in a forest ice ocean configuration. It's a quarter degree model, 75 vertical levels, hybrid vertical coordinates, and we have KPP for a vertical parameterization, and we have biharmonic SMAG and mixed layer restratification turned on. And so that's a control one. And then we have three experiments we have three experiments. And so one where we turn on backscatter, but we only turn on backscatter when we have at least when the deformation radius is resolved at least with half a grid where the deformation radius is larger than half a grid space, right? And then we have a simulation with only GM turned on, but the GM is turned on only in regions we're not resolving mesoscale eddies, and we define that as just the deformation radius is less than half a grid space. So this is the inverse condition from the one before, right? And then we have a simulation with GM and backscatter, and then here we apply GM when the deformation radius is less than half a grid spacing, and then backscatter when it's more than half a grid spacing, right? And just in a picture, is something like this. So in the GM only simulation, we're only applying GM in the light blue region, right? And in the backscatter only simulation, we only apply backscatter in the dark blue region. And then when we apply both of them, we apply one in the light blue region and then the other one in the dark blue region. So we're never applying GM and backscatter at the same time. And so why are we doing this? Well, first there's a theoretical reason behind this. When you're not resolving eddies at all, you want to turn on GM, which is what you do in a 1 degree model. And when you are resolving eddies, they're gonna be very close to the grid scale, so you want to energize those eddies, right? So that's the theoretical reason. But the real reason we're doing this is because when we turn on backscatter everywhere, we get a polynya in the Southern Ocean, which we don't want, right? And so we found that if we turn on GM with a resolution function, then we can eliminate this polynya. Okay, and so what do we see? What does backscatter do in our model? So we find that backscatter energizes eddies. It increases SSH variability. It reduces SST biases in the northern hemisphere, and we get a more barotropic ocean, right? And then we also see that it increases SST and SSS and NST surface salinity in the southern ocean. We have larger southward heat transport. It deepens southern ocean mixed layers and shifts them southwards. And so just a summary. And so let's start with SSH standard deviation. And so this is the measure of how variable your sea surface height is, right? And so you see in the upper left is the control and SSH standard deviation. And then I'm showing the GM minus the control, right? Backscatter minus the control, and then the GM and then the simulation with GM and backscatter minus the control. And then there's a thin black line that shows you the boundary between where I'm applying GM and where I'm applying backscatter. And so if you turn on GM alone, you see that you actually get less SSH standard deviation because of reduced variability because you're just killing your eddies as expected. And if you turn on backscatter, you see much larger SSH variability. And then when you turn on backscatter and GM, you see essentially a linear superposition of both effects. And then this is barotropic the barotropic kinetic energy fraction. So in this plot, red means your ocean is more barotropic, blue means your ocean is less barotropic, more baroclinic. And the control is shown in the top left again. Yeah, and then if you turn on GM, you actually see a less barotropic ocean. But when you turn on backscatter, you can see that these broad red regions where the ocean is becoming more barotropic, right? And then, yeah. Okay, and then for SST, what do we see? So when you turn on backscatter, you see that, you see in the northern hemisphere, you see this pattern of blue and red, and that's, this is improving the SST biases there, and this is already seen in other simulations. But the main thing I want to point out here is that you see this broad warming of the Southern Ocean, right? So the Southern Ocean just becomes more red when you turn on backscatter, right? And so this is a consistent response across all the different backscatter simulations. When you turn on backscatter, you just warm your Southern Ocean. And so this is the above images from plot is from the GFDL model, and then the bottom one's from Houssam 2. Skip that. Okay, and then for mixed layers. So here I'm showing the mixed layer. So the mixed layer difference between our simulation with GM and backscatter and the control. And what you see, so in red means your mixed layer shallows, and blue means it deepens. So you can see we had deep mixed layers further north in the Southern Ocean, and then those shallow, and then we get deep mixed layers closer to the Antarctic coast, right? And this is actually not consistent across models. So our mixed layers are shifting, we get deeper mixed layers that are shifted southward, whereas in TSOM2, you just get deepening to first, or you just get deepening mixed layers. So this is not a consistent response across different models. But however, on the continental margin, you see in both models, the mixed layers on the continental margin are shallowing because of the increased heat transport. Okay, and then so this is a map of it's a plot of global heat transport, and so the control line is the thick black line, right? And then if you turn on GM, you get this gray line, and if you turn on backscatter and GM, you get this like dark red line. And you can see, so in either, if you turn on GM or backscatter, you increase the heat transport to the southward heat transport in the southern hemisphere, and so I'll explain why we see it. So this is the overturning circulation, and so the top left is control again, and then the other three are differences between that simulation and the control. And so when you turn on, the most important thing to know here is what's happening at mid-depth in the southern hemisphere. And so if you turn on GM, you see you're weakening the mid-depth cell, right, at mid-latitudes. And similarly, when you turn on backscatter, you're weakening the mid-depth cell at mid-latitudes. And so the mid-depth cell, what it does is that, you know, it's transporting heat northwards, right? And so when we turn on backscatter, that mid-depth cell is getting weaker, right? And this leads to a larger southward heat transport, right? So this is the mechanism behind the change in heat transport. Okay, and yeah, just to restate what we saw again, when we turn on backscatter, we're seeing, you know, more energized eddies, larger SSH variability. We see a reduced SST biases in the northern hemisphere. We get a more barotropic ocean, but then we also see increased SST in the southern ocean, increased sea surface salinity in the southern ocean. We get larger southward heat transport, deeper mixed layers in the southern ocean that are shifted southward. And that's all I have for today. Thank you.
Thank you, Houssam. We got plenty of time for questions, starting with ECRs. No ECRs. Oh, there's one. Please go ahead.
Thanks. Excellent talk. I was just wondering, in the last couple of slides there when you showed the MOC, it looked like that might have been the Eulerian overturning circulation in the Southern Ocean. I was wondering, if you don't have GM, then you're not given the residual or the eddy-induced velocities, but you could still plot that as a overturning in density latitude space. I was wondering if you tried that.
So I haven't plotted it in density latitude space, but I know these are not residual. These are the residual, not the Eulerian. Yeah.
Yeah, very interesting. I was intrigued that in your Southern Ocean cases, the core of the ACC had lower kinetic energy and was less barotropic than the original, which is a big surprise. And I was wondering if maybe that's due to the proximity of the really strong GM region, and whether you might have considered having maybe a weaker GM coefficient to try and allow that to relax a little bit more.
Yeah. Okay. So we do have. So I have a simulation where we don't have. So I'm not sure if it's related to the GM region, because we have a simulation without GM, right? But with the resolution function applied, right? But I have also a simulation where I apply backscatter everywhere, and we actually see a more barotropic Southern Ocean. So I don't think it's GM. I think it's the resolution function itself somehow. But I don't understand the mechanism.
Very interesting. I've noticed that you had relatively little change of eddy kinetic energy in the North Atlantic current. Now your transition from backscatter to GM is just north of it. Is that a hard shift, or do you have a certain transition from backscatter to GM?
Yeah, it's a hard shift. Just a step function, essentially. Yeah.
There's one in the back, and then I come to you.
Hi, yeah, thank you. Very nice talk. I guess I'm wondering how, right, you just changed these things and you've not retuned the model at all. Do you have any feeling about how much the fact that the model hasn't been retuned is going to affect how realistic the outcomes are of doing these, changing the parameterization?
I think so. So I guess I'm trying to find the stage, but yeah, like I think you need to have, I think you need to tune the model before doing this if you want to have realistic results. Because, for example, our southern ocean is already too warm, right? So the control simulation has a very warm southern ocean, and then you turn backscatter on, you get an even warmer southern ocean. But I think backscatter is doing what you'd expect eddies to do, which is transport heat southward, let's say, right? So that part is realistic, but the end result is not, because the model's not been tuned.
Thanks.
Yeah, thanks. I have sort of a similar question. I mean, it's hard to argue that, or I guess I'm just looking at the SST biases and stuff that the model's improved, you know, in the Southern Ocean particularly. So should we all be using this, or what's the recommendation here?
The SST has not improved in the Southern Ocean.
No, not at all. Yeah, it's kind of gotten worse, right? Like,
yeah,
it's like significantly worse. So.
Right, yeah. I mean, but it makes things better in the Northern Hemisphere. So that's the current problem with backscatter.
So my question is along the same lines. I mean, what is it that you modify in the North Atlantic that makes the SST bias reduced? I mean, in general, it's in large part due to the Gulf Stream separating north, right? So is your Gulf Stream better? What's happening?
There's a paper, so the GFDL paper goes through this. I think what they do is, I hope I get the explanation right. So they basically apply backscatter in different regions, and they find that when you apply backscatter off of some geographic feature, Flemish, where's the Flemish cap? I don't know. But so if you apply backscatter in a certain region next to the Gulf Stream, it energizes the current, and I hope someone here can explain it better. But there is a mechanism that is.
No, I mean, you got it right. If the Flemish cap seems to be a critical region, and if you apply backscatter in that region, you energize the boundary current, and it manages to get flow around the Flemish cap better. I mean, I think one of the differences, in answer to your question about Northern Hemisphere versus South, I think it's that there are stronger boundary currents up against boundaries, and more of them in the Northern Hemisphere than we have in the Southern Hemisphere. The Southern Hemisphere, big currents are the zonal ACC. And so somehow the backscatter is acting differently on those mean currents, I think. The other thing is, do we really trust the forcing in the Southern Ocean as much as we trust the Northern Hemisphere? And that's another issue here, which is part of what Gökhan's going to deal with the EOA 5 and 6. But I wouldn't say that it's a parameterization we throw away just because it has a negative result in the Southern Hemisphere. I think we should look to see try and understand it better, because it seems like we all recognize we need to energize our models, and the fact that when we do that, we get a wrong result, a negative result in the Southern Hemisphere suggests we've got something else wrong.
I guess another just to add is when you backscatter, which length scales you'll be putting the energy back is another challenge.
All right, let's thank Houssam one more time. Next speaker is Dhruv Balwada from Columbia University. Dhruv will be talking about parameterizing mesoscale eddy buoyancy fluxes using a small neural network.
All right. Things work. Oh. Okay. All right. Thanks to the organizers for this great meeting. It's my first COMMODORE meeting, and it's really been an amazing experience. The work that I'm presenting today has been done under the umbrella of the M-Square Lines project that Lord gave a nice overview of yesterday. The part that I'm presenting is to do with mesoscale parameterizations. And here's a list of my co-authors. I particularly want to highlight Pavel Perzogin, who's a postdoc at NYU, and he's been very critical in much of the design and implementation of the work that I'm presenting here. It's been super helpful. Okay, so this has already been talked about in the past talks today, but the main goal that we have over here in this session is to improve parameterizations of mesoscale eddies or macroscale turbulence, which is turbulence on the scales of 1 to 100 kilometers. We know that these scales play an important role in transporting heat, momentum, tracers, setting the large-scale stratification, the energy cycles of the ocean, and so on. And that's the goal of our work. And so the goal here for what I'm presenting is to build scale-aware parameterizations that work over both eddying and non-eddying resolutions. How close we get to it, I'll show you now. And so to start out, I think first it's important to just recognize that the framework that I'm working in, how we define what eddies are and what their effects are. The goal is to parameterize the effect of the eddies on the larger resolved scales that we'll see in a coarse model. In particular, here I'm working with the thickness equation, which is part of layered models, and the way that we differentiate between what's large scale or resolved and what's eddies is by applying spatial filters. So when you apply a spatial filter to the thickness equation, you get some terms which correspond to your large scale thickness fields, and then you get these extra forcing terms that are subgrid. Traditionally, these subgrid terms have been parameterized in terms of advective form, where you have a stream function to represent these effects, and the Jensen-McWilliams parameterization would parameterize this advective stream function using a diffusion operator. And our goal is to see if we can use some data-driven parameterizations to do better than what GM can do. It's also important to sort of remark on one aspect of what we are doing here that's different from the two talks that came before. So conventionally in our field, what we are doing is, what you might call like functional parameterizations. We understand that the eddies have some function that they're playing in the physics of the system, like reducing available potential energy or, throwing energy from small scales to large scales and so on. What's a little bit different over here is that we care much more about the structure details of these terms that you diagnose. In the LES literature, it's called structural parameterization. So we care about predicting the right subgrid fluxes in the right place and having the right relationships to large scale. So it's a subtle difference over there. The eventual goal is the same, to make large scale models better. The general process that we follow is that we will run some high resolution simulation. Here an example is shown from an idealized two-layer Phillips channel in MOM6. We will apply a spatial filter. This will give us the large scale field at different filter scales or different large scales. Correspondingly, we can also diagnose the subgrid forcing. Once we have the subgrid forcing and the large scale fields, we will try to build a functional relationship between them using some machine learning method. The next step would be that we can also run the coarse resolution simulations for the same setup. And the hope is that when you plug in the subgrid forcing function that you learned using machine learning, it can help the coarse resolution simulations get closer to the large scales of the high resolution simulation. Now, one thing to remark over here is that if there is a relationship that exists between the large scale and the subgrid forcing, which here is the subgrid thickness fluxes, you can throw any machine learning model at it with a little bit of playing around, maybe for like a day. Some functional relationship will be learned if there is one to be learned. So it's not a very hard problem in that sense. But if you do that, often the problem that you face is that the model won't generalize to any other regime except the data that you trained it on. And so we want to try and build in some more characteristics into these functions with the hope that there is some generalization of the model to other setups or just sort of other parameter regimes. And so the way that we go about doing that is that we initially chose that we are going to build point-wise models, which means that we're going to predict subgrid fluxes at a certain point using points that are within the vicinity of that. So maybe the points that are just in a 2x2 stencil, 3x3 stencil, some like very, very closed domain this was for practical reasons because we want to eventually implement it into a model and we don't want information coming from 500 grid cells away. Also, it seems to not make very much physical sense. The other choice that we made is that we're going to try and parameterize the subgrid fluxes using a set of input features or input variables that were chosen based on some physical intuition that we have about the system. So we expected that things like the large-scale velocity gradients might be important in the horizontal direction. Large-scale thickness gradients might be important. Maybe the resolution of the model might be important. We want to build in some scale awareness into the system. And then we took a few extra steps that I'll go through one by one. Each of them is sort of a design choice with the hope that each one helps you in a certain way or at least constrains the model to work well. So the first thing that we do is that we do some non-dimensionalization. What that means is that we take our input variables and we create some non-dimensional functional groups out of them. So, and to test whether this works well or not, I'm showing this figure over here, which is showing you the distribution of the subgrid flux that we are trying to parameterize. The different colors correspond to the subgrid fluxes in different layers. On the x-axis, we are showing different filter scales that we filter the model with. And if this bar over here is a little bit thicker, it means that there are more points over there. It's basically a distribution function. And the red dots show the median of these distributions. And the other thing to note is that this is on a log scale. So you have basically very large or very variable distributions of subgrid forcing. When we do our non-dimensionalization, we see a few things that happen. One that, and so the non-dimensionalized subgrid forcings are shown in these lighter colors. And so basically what you see is that across a range of filter scales, the distributions align together. Across different layers, the distributions align together. And also for many, many cases, the distributions get narrower. And so it'll be easier for a machine learning model to predict narrow distributions rather than when the values are spread over orders of magnitude. And this is a log scale. So for example, here at this filter scale, we went from like about 5 orders of magnitude down to 2, which is a nice thing. When we do the same kind of non-dimensionalization for the other inputs, we get another interesting thing, which is that, so for example, the velocity gradient tensor has multiple components to it. When you non-dimensionalize it, you kind of split it up into 2 parts. There is a part that corresponds to the sort of the norm of the tensor, and then there is another part that corresponds to the orientation of the tensor. And the orientation elements become range limited to be between -1 and 1. This is another nice feature for a ML model that you won't ever see inputs to your model that'll be outside this range of -1 and 1 because you did that by construction. What you do with the magnitude is a little bit of a matter of choice. In our non-dimensionalization, the magnitudes for the velocity tensors automatically got out of the function. For the thickness gradients, we sort of did a separation of variables where we said that there's some part that corresponds to the orientation of the thickness gradients, and then there's some part that will correspond to the magnitude of it. And we'll learn some of these functions and we'll set some of these functions based on prior expectations. Another thing that we did is coordinate invariance. So, we're learning on a model that's on a Cartesian XY grid. Obviously, our model physics doesn't care about that. So before doing the learning, we rotate all of our outputs and inputs into a new coordinate frame. You can do it for any flow-dependent coordinate frame. We chose one here that made sense for this problem, which was that we went from XY to a coordinate frame that's aligned with thickness gradients. One nice thing is that now you have coordinate invariance, and the other nice thing is that one of the new sort of subgrid fluxes that you have is oriented in the along gradient direction, and this has a physical meaning that this corresponds to the variance production or dissipation in the system. And you can imagine that at some later stage, you might want to be able to have more control on this if you want stability in your model. Then I also said that we were building in scale awareness by adding in input functions that corresponding to the grid scale of the model. So the test that we did was that if you build a single model with a scale parameter as one of the inputs, how does that model compare to if you build separate models for different filter scales? And that's shown as the black and blue line over here, which basically overlap. And so the main idea is that if you build a single model, it performs almost the same across all filter scales as if you were to build independent models for all filter scales. And the things that I'm showing over here are the model scale in terms of things like the R2 score or the correlation of the model. And the main idea is that the machine learning model has a lot of skill on these metrics across a range of filter scales. And obviously by design, works better than other models that were either structural or didn't have non-linearities in them. We also did some testing to understand how much of a lateral domain you need information from. And so we tested a model on where we have input stencils of 1 by 1. So you're trying to predict the flux at a certain point using the gradients at that point. What if you try the gradients from a 3 by 3 stencil, a 5 by 5 stencil? And basically what we find is that as we include a little bit more non-locality, the model skill improves, but it doesn't just keep improving forever. Somewhere between a stencil of 3 by 3 to 5 by 5, the model skill saturates and you can't, it's already very, very high. And so it's hard to do better than that for this offline metric. And the final thing that I don't have a slide on is that the machine learning model that we're training is a very small ANN, so it takes these 6 or 7 inputs that we have, input variables, and 2 output variables. And the neural network itself might have something like, for machine learning, it's like 1,000 parameters, and it's very small. It's not something like millions. Again, part of the reason for doing that was we didn't want to make a machine learning model that was so expensive to run that it becomes, overpowers even your entire GCM, which might happen if you had a very deep model. Okay, so once we did all of that, we implemented this neural network into MOM6. Since it's such a simple model, it's something that's very easy to do. Same thing that Jan was saying, that if you build simple models, you can put them in very easily. And we did, for now, testing on similar setups as the ones where we had trained them on. And so this is one nice idealized test case of Phillips 2-layer that comes from Bob Hallberg's paper in 2013. And the main idea is that you force on your model, your eddies start to disappear. And in this particular setup, what the eddies and the resolved flow are trying to do is that they're trying to create a overturning circulation. And so as the eddies become weaker and weaker, your overturning gets weaker. And so what we hope is that we can build a parameterization that can get you the right overturning circulation. Another problem that was pointed out in this setup was that you can use GM to do the same thing, but when you use GM, it kills the resolved flow, which was the problem that Houssam was also pointing out earlier. And so we want something that doesn't kill our resolved flow, but can get the right overturning, along with it. And so this slide over here is showing a number of test cases that we ran. We have our high resolution simulation at the top. The second row is showing a number of non-parameterized simulations over different model grid scales. And then the next 2 rows correspond to the ANN that's been implemented into the same setups. And so we see a few things over here. One, that when we turn our ANN on, there's a slight reduction in the eddy strength, but it's not dramatically lower. It's not the case that we end up with no eddies at all. Another thing that we see at really coarse resolution simulations where you have no eddies at all is that when we put our parameterization in, there is some variability that gets generated, and which would not have shown up if you were using GM. We also test for our bulk properties, and so what's shown on the left side is the overturning circulation as a function of the model grid scale, and basically as your models get coarser, your overturning gets weaker. When you put the ANN in, you can get the overturning, back to some control setup that you care to reproduce. Obviously, there is some tuning that had to go into doing this, right? It's not like you can just build a parameterization that would work with no tuning. I'm not going to go into this figure very much. I don't think I have very much time, but there's some key points that are key takeaways, right? That one, we have built a new parameterization that is some sort of nonlinear function. It's not like GM where you can easily think about how the parameterization or how the resolved flow is going to respond to it. So at this point, it becomes almost like an empirical testing of like, what is this function that you have generated? And you can probe this function to try and understand this a little bit. It's not something that you can do with theory very easily, at least not at the state that we are in right now. What we also find is that the resolved flow in this, so when we do this probing of this machine learning model, we find that the resolved flow responds to the tuning coefficient. Generally, what we find is that the eddies are not damped as badly as they would be if we were using Jensen-McWilliams parameterization. Another thing that we find is that the response to the resolved flow is relatively nonlinear to this function's strength. So it's not the case that you increase it and it just like monotonically drops. It's sort of a function of your coarsening scale or your model grid scale and so on. And so there's some things to test out, but generally you can tune it to do well. In conclusions, we are developing parameterizations based on some machine learning and some physical intuition that we have about the system, hoping that these models can perform a little bit better than our physics-based models or a purely machine learning-based model. You made a new function, so obviously you would need to study it empirically to see what it's doing. There's no surprise over there. Response to the resolved flow in the test cases that we run is stable and favorable. I should also say that we did similar tests on a 2-layer double gyre setup, and we're able to get successful results for that as well with some tuning. And when we build in these extra features, there is some generalization of the model. So we have done tests where we train the model on maybe Phillips 2-layer and then try it on our double gyre simulation. What we find is that there is some generalization when you have some eddies resolved. But if you have gone into the regime where there is absolutely no eddies, there is not very much generalization, even with these effects built in. So going forward, there's many steps that need to be done. One thing is that why is there no generalization? It's maybe because there's absolutely no information in the 2-layer channel simulation for the large-scale setups that you're seeing in the double gyre, for example. And so if we train on a vaster data set, maybe coming from global simulations or idealized simulation done over large parameter regimes, we might be able to alleviate some of these things. It's just a hope. We want to merge thickness and momentum parameterizations. Jan talked about it earlier, and Kelsey is actually going to give her next talk on this topic, on the work that she's been doing on this. Another important thing is that the machine learning model that we built had these input features that were not very much related to the parameters that we often think about, right? We think about things like deformation radius, beta effect. None of those have been incorporated in explicitly into this model. So if they are part of the large-scale flow, they are there, but there is more work that needs to be done to sort of bring them in. I know Pavel's been working on this a little bit, but it's still very much work in progress. And then finally, right, like a lot of the choices that are made in what we have done have been very empirical and sort of like, let's try the easiest thing. There's not a lot of theory on how to do the right discretizations and so on. And so there's a lot to be done along those lines. Thank you.
Thank you, Dhruv. We have 1 minute for questions, starting from ECRs. Andrew.
Hi, that was a really nice talk. I just had a question about your rotation onto the direction of thickness gradient. How are you estimating the gradients in U at that point then, right? From the staggering of the C grid, and then are you interpolating and then calculating the gradients?
Yeah, that's a good question. So I did sort of gloss over that detail, and that's why I also have this choice of discretization and so on as future work. So right now what we're doing is very simple. We bring everything to the same grid point, and by interpolations, and then do rotations over there. And when we go to implement in MOM6, we are doing the same thing. We take the features in MOM6, first bring them onto the center point, apply a machine learning model, and then extrapolate them out back to wherever they are needed in the setup.
So is there potentially then so when you saw that it just kind of like energized the flow, is it potentially that you're essentially introducing some noise when you're doing that rotation, projection, interpolation, and that's a cause for the re-energization of the flow?
It's possible. Yeah, I'm not sure.
Yeah. Quick,
So
please.
you had you did a subsequent, like a second tuning, a second calibration basically, but you only tuned one parameter. I'm wondering if you know, do you think it would help to tune more? You said you had 1,000. So
Oh, right. So
it's not in your future work. So and do you have a way of figuring out which of those 1,000 might be promising to pick?
yeah, so in this work right now, that actually none of those 1,000 parameters have been tuned. What we have done is that we get a prediction. They have been trained, right? But we get a prediction, and then the tuning coefficient is just an amplification factor on top of this. But yeah, obviously going forward, you need to, have some more systematic way to do that. The approaches that you are doing may be helpful for that. Yes, then you can retune the entire network.
Let's think Dhruv one more time.
Another email went out this morning at 8:43, and we think that it is up to date. Could you please check your email that you received? This is only for Friday. So people who are registered for Fridays, we think that this is the list. So if you haven't received it and you think we registered for it, please send me an email.
8:30.
At 8:43 Mountain Daylight Time this morning. Okay,
Yeah, so we will be back here at 10:30. It's a shorter break today. See you soon.
So 2 emails from Elizabeth, but neither of them to do with what we're talking about.
And here's our pointer, and you might have to wake it up because they call it saving information.
Okay.
Pointer, next certificates, if you want to have this pointer.
I was doing that on the break. Thanks.
Thanks. All right, let's get started. Our last talk for this session is from Ian Grooms from University of Colorado Boulder. Ian will talk about the stochastic GM plus E closure, a framework for coupling stochastic backscatter with the Jamet-McWilliams parameterization.
All right, thanks, Gustavo. Can you all hear me? The mic working? Yep, all right. I'd like to start by acknowledging my collaborators, many of whom are in the room here. So Niraj is somewhere in here. Gustavo's down front. Houssam Yassin is in the back. Phil Pejon is not here in the room, but he's here in Boulder. He's at the NOAA Physical Sciences Lab just down the hill. So I'm going to talk about parameterizations for non-eddying models, which are maybe not as exciting as eddying models or even machine learning models. But my apology here is that I think these models are still important and they're still going to be with us and used for a variety of purposes as we move into the future. And so it's still worthwhile to try to make them better. So brief apology there. What could you do to try and make these things better? Well, people have been working on these models for decades, trying to make them better, and there's lots of things that could be better about them. The thing I'm going to focus on in this talk is variability. These models are deficient in variability. So when you think about the real ocean and its variability, you have atmospheric force variability and you have ocean intrinsic variability, and these models have a good amount of atmospheric force. That's not so much of a problem. They do have some ocean intrinsic variability, but in the real ocean, a lot of the variability, the ocean intrinsic variability, is associated with mesoscale eddies. And these models can't have mesoscale eddies because of their grid size. You just can't put a mesoscale eddy into a non-eddying model. So they're not going to have that variability. It's unavoidable. That being said, there is a component of an ocean intrinsic variability that's driven by mesoscale eddies, but that exists on length scales that are resolvable in the model. And that is not unavoidable. That's something we can fix. We can try to get the large scale variability to be more accurate. And as you might expect, we're going to use backscatter to increase that variability. We do it by injecting energy, and from the energy comes the variability. We've heard a lot about backscatter already in this conference. There's a lot of backscatter schemes. Many of them are designed for eddying ocean models. So you have a model that permits eddies, at least, and then you have a backscatter scheme to try and improve them, to make them more energetic, more realistic. The paradigms, the sort of physics that underlies the construction of those backscatter schemes is not really appropriate for a model that doesn't have any eddies at all. So rather than just trying to turn those schemes on in a non-eddy resolving model, I'm going to try to look for something that has a better foundation that's more appropriate for a non-eddying model. And there's a couple, and the one that I'm going to draw on is from a paper by Scott Bachman here. So non-eddying models have a GM parameterization, Jen McWilliams. It removes potential energy from the resolved scales. And then you have to decide what you want to do with that energy, if anything. And so in Scott's paper, he said, all right, GM is removing energy at a certain rate, which in MOM6 parlance is called the GM work rate. And so we're going to take a fraction of that, some percentage of that rate, and re-inject it using backscatter in the form of kinetic energy. The other paradigm that I'm not going to rely on is GM is taking energy out at a certain rate, and you dump that into a subgrid scale energy budget. And then you try to backscatter where the rate of backscatter is tied not to the GM rate directly, but to the amount of subgrid scale energy. I'm not going to build on that, but that's an interesting and related sort of paradigm for this. So how did Scott actually do how did he implement the backscatter? He used a negative viscosity, which is again something we've heard. Most of the negative viscosity backscatter schemes combine a negative Laplacian viscosity with a damping by harmonic term. Scott didn't do that. He applied the negative Laplacian backscatter to the barotropic part, which I'm representing with the angle brackets there. And then you also have a Laplacian dissipation on the baroclinic part. Okay, so he implemented this in MIT GCM. So the paper on the previous slide, he showed results from MIT GCM in a nice zonal channel model. He then implemented it in MOM6, so it's in MOM6, did some testing in a global configuration, didn't write a paper. I was not party to that. I was not part of that effort, so I can only speculate as to what happened. And I will speculate as to what happened. So we've got GM and backscatter, and both of them are deterministic. And in certain limits, they're both sort of linearly damping or linearly amplifying things. And so you have a competition between different linear effects, one damping, one amplifying. And our experience in the eddy energy CPT has been that it's kind of hard to get backscatter to work when you have GM turned on at the same time in the same place. That competition of amplifying versus damping, GM tends to win. And I suspect that that was contributing to the difficulty in getting the GME scheme to work well in the global configuration. Houssam's talk this morning, you can get around this in an eddying model by having GM turned on in some places and backscatter turned on in other places, so they're not directly competing with each other. But in a global model at coarse resolution, you can't really do that. You need GM everywhere. So in order to get effective backscatter, we basically need to rely on something other than negative viscosity. And we're going to do stochastic backscatter. So, you know, Scott's momentum equation, backscatter in there. I'm just going to replace that with stochastic forcing. The scheme I'm going to call stochastic GME, because I'm going to construct my stochastic forcing in such a way that the rate at which it injects kinetic energy is some fraction of the rate at which GM is removing energy. And you could do other things, but since that's what I'm doing, and it's basically the same thing that Scott was doing, we're going to call this stochastic GME. You can think of this as a forcing term in the momentum equations, but that's not actually how we implement it. We don't actually monkey with the momentum tendency or the velocity tendency. We just let the model take its steps, and then in between steps, we add a stochastic increment to the horizontal velocity field. So in order to tell you what this stochastic scheme looks like, I need to tell you what the increments look like. So they have some amplitude, some magnitude. They have a horizontal structure like a horizontal length scale, a vertical structure, a time structure. I'm going to skip a little bit ahead and talk about the horizontal structure first. So what we do is we use spherical harmonics, and this is implemented outside of MIT, outside of MOM6, sorry. There's an external package that does the spherical harmonics. And you can use any spectrum you want for the spherical harmonics. What we're doing is we're generating a random field that has a flat spectrum at large scales, and then it drops off. It's a Gaussian decay like that. We evaluate that field on the Gaussian grid and then interpolate it to the model grid. So we have a random field with a certain spectrum. We then multiply that random field by the amplitude, and the amplitude is constructed so that the kinetic energy backscatter rate is proportional to the GM work rate. And you'll note that I've got the word smoothed in there, and that's important. So here on the top is a monthly average depth integrated GM work rate from a low-res simulation, and you can see it has some fine scales in it, at least fine, compared to the grid size of this model. And what we want is we have a random field, and we want to modulate that random field. So it's got some variability, and then you multiply it by a slowly varying modulation. And if you use the GM work rate as it is, it's not slowly varying compared to the length scale of the random field. So there's not enough scale separation between the GM work rate and the grid scale of the model to have the random field sort of sit somewhere in between. So we need to smooth that out, and we do, and you can see on the bottom what the amplitude field looks like for this same month, and you can see it's a lot smoother. This is possibly the most expensive part of the parameterization because we have to do a fair bit of smoothing on this two-dimensional field, which involves a fair bit of communication. So that's the horizontal structure, the amplitude. We've taken a random field, we've multiplied it by the amplitude. We then take the derivative of that and let the x derivative be the y velocity and minus the y derivative be the x velocity. And that way we get an incompressible velocity increment. So we are not generating any vertical flow with this stochastic increment. When you do that, so I started out with a random field that's flat and drops. When you take the derivative to construct the velocity increments, the spectrum now starts at 0, rises to a peak, and then drops back again. And we can control, I'm going to talk about the length scale of this thing, and it's the peak of that spectrum that I'm talking about. The vertical structure, so we don't do a different random field at every depth or at every model level. We do one two-dimensional random field, and then we multiply it by the first surface mode. The surface mode is like the first baroclinic mode, but shifted so that it's 0 at the bottom. Inside MOM6, it's also called the equivalent barotropic mode or the equivalent barotropic profile. The time structure is simple, just AR1, autoregressive order 1, which means it has an exponential decorrelation function. And we want it to be fast. So we need it to be fast. We've chosen to make it 6 hours. The reason it needs to be fast is because we want to be able to precisely control the kinetic energy backscatter rate. Pointer's not working. If you have a random forcing that decorrelates slowly, and the decorrelation time is comparable to the flow time scale, you generate correlations between the forcing field and the flow itself. And those correlations make it hard to precisely control how much energy you're injecting at any time. So we want it to be fast for that reason, so that we can control the energy injection. All right, we've implemented this thing, and I'm going to show you some results from a MOM6 simulation at the workhorse 2/3 degree resolution, 65 Z-star levels, ocean ice, atmosphere forced. We're using GM and Reddy. The amplitude of both of those is set with the geometric scheme. Ready is depth independent. GM has this first surface mode vertical structure. We spin up from rest for 60 years. Then we branch off the experiments from that. We run for 62 more years. I'll show you diagnostics over the last 50. There's two parameters that I'm going to vary. One is the length scale of the stochastic forcing, and the other one is how much of the GM work rate are we going to pump back in with backscatter. So I decided not to try to show you a movie. So I'm showing you just snapshots here of the South Atlantic instead, and this is surface speed. Top left is the control, and you can see, you know, there's some structure in there, but it's fairly smooth. Top right is stochastic with a length scale that's 125 kilometers. That's a wavelength, by the way. And the grid size in that region is on the order of like 30 kilometers. So this is fairly close to the grid scale. And it's definitely working in the sense of generating variability, but maybe too well, right? Maybe too much. That's a little bit of a rough field. You get to where you think maybe the numerical scheme for advection is going to be generating spurious mixing when your velocity field is that not smooth. So in the bottom left, I've got 250 kilometer length scale, still a good bit more variability, spatial variability than the control, but not so rough that we're worried about numerics. And then bottom right is 500 kilometers, and there's more variability than the control, but not much more. The problem with making your length scale very large on your random field is it gets to be so big that it's, again, getting close to the length scale of the modulation field. And if you have a random field and a modulation field and they're both the same length scale, then the modulation field is not modulating, right? So 250 is sort of a sweet spot here. Top left here is going to be the temporal standard deviation of sea surface temperature from an observational product after detrending and removing the seasonal cycle. Left middle is the bias in that quantity in the control run, and it's blue, which means that we have too little variability in SST almost everywhere. Yeah, there's some spots where there's too much, but mostly too little. In the right column is the difference between the stochastic runs and the control runs. We want the colors to be opposite so that you're reducing the bias. Note that the color scales are different. So we are reducing the bias, but we haven't completely removed it. I'm only backscattering in all of these results here 50% of the GM work rate. The top there is 125 kilometers, the bottom is 500. The top one is not as effective at generating variability. So just like over here, we had lots of sort of small scale structure in the velocity field. That one doesn't generate temporal variability as well as the ones that have a longer length scale. This is the same thing for sea surface height, OBS product on the top left, bias in the middle left, and then the difference between the control and the stochastic ones in the right. And we are improving the bias. Again, we don't completely remove it, but we do improve the bias in the places largely where it needs to be improved. That was varying length scale. This is varying just the magnitude. How much of the GM work rate are you backscattering? On the left is the amplitude of the backscatter. The top is if you do 25%, the bottom is 75%. You can see that the amplitude goes up, right? So no surprise there. On the right, though, I've given you kappa GM. And I'm putting this slide up here because there's a caveat here. So if you're taking 75% of the GM work rate and you're backscattering it, then you should really only put 25% of that GM work rate into the submesoscale, or not submeso, subgrid scale kinetic energy budget. So you're generating less kinetic energy when you do that. And the kappa GM depends on the subgrid scale kinetic energy, and so it's going to go down. And so I retuned these simulations to avoid that. So I had to retune the geometric alpha coefficient so that the kappa GM would sort of stay approximately the same as I'm changing the amount of GM work that gets backscattered. And whether you should do that, or if you do want to do that, what's the right way to do that, are still open questions where I don't have a plan, only concepts. So we have submitted this to James, and the preprint is on the Earth and Space Science Open Archive, and I'm happy to take questions.
Thank you, Ian. Questions from early careers?
Hey, Ian. Nice talk, Dan. So I was wondering about your injection of, so you define this horizontally non-divergent fields, but I'm assuming that because you're not introducing a density anomaly as well, that will be unbalanced, meaning it would tend to project on internal gravity waves.
Yes.
And 125 kilometers to me sounds a lot like typical mode 1 internal tides type scales. And so I'm wondering if there's something like unbalanced motions that's happening there. And that would be the question. Number 2, if so, is there some way you could generate balanced perturbations by doing something to the density rather than just this kind of unbalanced velocity only perturbation, or is there some problem with that general trajectory?
Great questions, thank you. Yes, the flow that we're putting in is unbalanced. And so there is an adjustment period where gravity waves in particular are being radiated. And I've done some sort of back of the envelope theory for how much of the energy that we're putting in is going to sort of go into the unbalanced field. And I think it's like half at these length scales, which is kind of a lot. But we don't actually, I have not seen any evidence of detrimental effects or even of large wave energy in the simulation. And so I'm not sure that the theory is exactly correct. The theory is based on just a sort of a quiescent, you don't have a background mean flow. And here we always do have a background mean flow. And so maybe the theory is not exactly correct. Could you generate balanced perturbations? I'm not sure how to do that practically speaking in a way that's not just hard, you know. You could instead put your backscatter not in kinetic energy, but in potential energy using a stochastic Jet-McWilliams type thing. And then at these scales, conversion from potential to kinetic is actually quite inefficient. And so you wouldn't get as much conversion if you did that. But that's, you know, a separate scheme, something different from what I'm doing, I guess. Great questions, though. Thanks.
Thanks for the talk. I had a similar, but hopefully perhaps simpler question just about this. Horizontal scale is laterally incompressible, so I guess it's like a stream function. But then when you impose the vertical scale, and if that first surface mode, the structure of that surface mode varies and as you move horizontally, doesn't that impose some divergence?
Yes, it does. Yes. So there's an asterisk. It's not completely laterally incompressible, but the EBT mode does vary pretty slowly. And so the divergences that you're introducing are pretty weak. So the vertical velocities you're introducing are weak. The one other thing that we do, which I didn't mention here, is near a boundary, we taper this thing out so that you're not introducing flow normal to the boundary. And the tapering is weak, but it also kind of screws up the lateral incompressibility. So you do get a little bit of divergence near lateral boundaries. Good point, though.
Thanks, Ian. I think it's me, right? Yeah, the length scale, the 250 kilometers, it was constant globally. The amplitude scale is not. Can you sort of give the thought process behind that and why the latitudinal, or why there's no spatial dependence to the length scale?
It's just hard to make a spatial dependence, practically speaking, on this grid. You can do it, and the stochastic physics package that I'm using has the capability to generate multiple random fields with different spatial length scales. And then we could update the parameterization to take sort of different combinations of the different fields at different latitudes so that you're effectively changing the length scale as you change across latitudes or regions. But we haven't done that yet. Possibly future work.
You introduced this as something for non-eddying models, but I see no reason why you wouldn't want to consider this also for the eddying models.
Yeah, the question is what's a good way to set the amplitude of the backscatter if you're in an eddying model? And I think this is a good way to do it in a non-eddying model. Is this the right way to do it in an eddy permitting model? I'm not sure I want to make that case, but the code is there and you could certainly turn it on in a quarter-degree model. And we haven't really done that yet.
Okay, thanks, Ian. We have now time for discussion. I'd like to thank our note taker for this session, Manita. Thank you so much for taking notes. Sure, yeah. So I also suggest, so we didn't have time to ask questions for Jan, so we can use this, 2 or 3 minutes. All right, so let's pretend we just finished. Who has a question for Jan? Yeah.
Okay, so Jan, I was wondering about if you implement this in a model and you need to decide whether to use the prograde or the retrograde parameterization. I guess you need to calculate the isopycnal slope near the boundary. I was wondering, like, first, how do you do that? Would you just use like very local grid information, or would you try to smooth it out? Because often, I guess, a slope, isopycnal will tilt one way and then intersect normal to the topography. And then a sort of follow-up question is, are the parameterizations between the prograde and the retrograde, do they meet continuously? So if you understand that, yeah.
Yeah, thanks, Jeff. So second question first. They do converge together when the topographic slope just vanishes. So basically, the converged, we intentionally make these schemes converge to the conventional scheme, existing schemes, people are using now. For the first question, that's a good one because it's also depending on how we define topographic slope at the large scale and also the roughness at the smaller scale. So I imagine that we could do some one-time filtering of the large-scale topography. And also I'm thinking that if we're using this into a coarse grid resolution model, basically the grid size helping us to filter out all the topographic roughness, then we can basically using what's resolved in the stratification to determine whether we're in a prograde or retrograde regimes, things like that, but also up to testing, yeah.
Hi, Jan. Enjoyed your talk, thank you. My question is about the vertical structure of the buoyancy flux. I hope I didn't miss it in your talk, but it seemed like you were mostly talking about the magnitude. And it wasn't clear to me if there was a vertical structure and if it was, do you have any insights on what's an appropriate vertical structure in this kind of a situation?
Yeah, that's a great question. Basically puzzling me for years. For most prognosis online testing cases, we're basically using a vertically invariant fluxes. It turns out to reproduce all the leading order structures that we want. With the question of regarding how to parameterize the vertical structures of eddy fluxes, there are possibly 2 ways that need to be tested. One is to prescribe the vertical structure of the energy itself, then the energy structure feed into the fluxes itself. The other one, we also diagnose the flux vertical structures, which turned out to be extremely vertically surface stratified, surface intensified, actually. It can be captured by, for example, all those classical linear existing modes we're using now, including the SQG or any QG based. So that's still open question, I guess. Yeah.
Thank you. Okay, let's move to the discussion part. These are the questions we have posed. Again, some are meant to be debatable and provocative. So first question, are mesoscale eddies parameterizable? What are the main barriers hindering progress in improving mesoscale parameterizations in ocean models? Number 3, how can we leverage machine learning techniques to improve the representation of mesoscale eddies in the ocean models? And number 4, do we have a better way of selecting the scales of interest? What are the best practices approaches for scale selective parameterizations? All right, so who wants to start? With Andrew, then Andy.
So I'll answer, or I'll comment on number 2 from the perspective of the NEMO Eddy closure working group. So this is actually a topic of conversation that we've really had a lot of conversation we've had many times with the members of the group. And one of the things that we see is that there's a lot of interest in the academic community to try to improve mesoscale representation, to come up with theories, come up with parameterizations. But one of the problems is, how do we actually evaluate the parameterizations? Because there's a difference in compute scale that academics have access to in general versus where we actually use these mesoscale parameterizations. And so we'd ideally like to use them in a 1/4 degree or 1 degree model, but you know, that's expensive for an academic to run a 1,000-year simulation for spin up or whatever. And so the question becomes, what are the appropriate test cases, even if they're not complete, you know, for every single Eddy diagnostic or every single Eddy process? What is at least a group of test cases that we as an entire community can agree on and also implement in our various modeling systems? And then the second part of that, which is the flip side, is, do we have any metrics, or what are the base level underlying metrics and diagnostics that we need to report, so that when we write these papers, we're not comparing a channel model to a QG model to a 1/4 degree MOM6. And that's the kind of conversation that we've been trying to have, at least in the NEMO Eddy closure working group.
Do you want to address that? Okay. Does anybody want to comment on that?
I recall at the last Commodore workshop that the Commodore leads were going to write a paper talking about test cases to do that. I'm partly sarcastic, but maybe that is something that we just need to keep in mind. I mean, that would be various things, numerical and you know, eddies and so forth, but test cases and having people run from the mathematical community to the global modeling community, having these test cases well known, well defined. Yeah, the Ocean Model Development Panel. We can let them take care of that.
Can I add to that? Sure. Essentially, another thing that it occurred to me this morning, that many of the initial testings are being done in whatever double gyre configurations and idealized, and even with Ian's global implementation, I still don't know whether that parameterization is beneficial or not, because it needs so many other diagnostics to be able to judge these things. I felt like we need a translator between these, what's presented, and what can get into the global models, because I see benefits, but there were so many other issues that I can see that they were actually degrading the solution. So how do we essentially address that in a systematic way? I think coming back to Steve's point again.
Yeah, I might pose my question, which I think may give us some hints on that. And I'm really only qualified to speak from a Southern Ocean perspective, so I'll start with that. And in my view, there's 3 things that eddies do. Firstly, they do the interfacial form stress, which is closely connected with the thickness fluxes. And that's what we often think about in terms of the eddy parameterization. Kelsey showed they also do the momentum flux, and maybe I won't delve too much on that, but eddies also do isopycnal stirring, which creates isopycnal mixing, and that's particularly important in the Southern Ocean, but perhaps less important in either the test cases people are using or the other regions. And so my observation of either Ian's case or Houssam's case is that when you put the backscatter energy back in, you're adding back energy, and that's all you need to do the form stress part of what eddies do. But if you look at Wender's poster out there, you'll see you get very circular eddies at a 1/4 degree when you inject the energy back in. And so you're missing the shape of the eddies. And I think it's that shape that's really important for the isopycnal component. And so I think if we're thinking about metrics and if we're thinking about processes, we have to evaluate all 3 things: the momentum, the horizontal momentum flux, the vertical momentum flux, which is the form stress, and the isopycnal stirring and the effect that they have on the solution. And I sort of disagree with Alistair's previous comment about Houssam's work. my hypothesis for why the Southern Ocean SST is not as good there is probably because the isopycnal stirring is not doing very well. So I think that's my rant for the day, and I'll leave it to others to comment.
Yeah, so I'd like to.
Does anybody? Was not necessarily. So then at that point,
Yeah, I'd like to address a little bit number one. I mean, do we really truly understand what mesoscale eddies do? And as we increase resolution, how is the large scale circulation? Is it just a response to mesoscale eddies? Or do you have, can you truly isolate what mesoscale eddies do in the circulation?
I would also like to address number one. I think in the world of subgrid scale parameterization for fluid problems, a lot of progress can be made by dealing or by assuming some sense of universality. So if you're looking at, for example, homogeneous isotropic turbulence far from a boundary, the forward cascade, there's a sense of universality there. It doesn't matter, if it's large scale, small scale, the setting of the external domain sort of doesn't matter. The turbulence itself is universal. And I don't think that we have that when you're thinking about mesoscale eddies. They know where they are. They know if they're in the Southern Ocean. They know if they're in the subpolar gyre in the North Atlantic. They know what beta is. They know what topography is. They know what all those things are, which makes it a lot harder to parameterize them. But I still think they are parameterizable. And I think that, Jan's talk is a great example of confronting the complexity head on and saying, well, for this specific situation where the eddies know that they're on a slope front, what can you do? And I think in order to successfully parameterize eddies, you have to do more of that.
Just a quick comment on Eric's question about where do we expect mesoscale eddies are impacting playing a major role, especially mainly if we look at the horizontal buoyancy flux. If we plot the spectra of that, you can see a significant peak due at the energy containing about the mesoscale scales, which means that at that scale, it's really the mesoscale eddies at that scale are dominating the buoyancy flux, especially horizontal buoyancy flux. And also momentum flux, you can do a similar analysis. I believe probably it's also mainly the mesoscale eddies are dominating the eddy mean flow interaction energy flux. But for vertical buoyancy flux, maybe not. Maybe it's more as you go to smaller scales, the vertical buoyancy flux is larger. Maybe some mesoscales or other turbulence processes are more important.
I'm worried this is going to be a dumb comment, but is it going to be easier to work on eddy parameterizations or rewrite code so they can run on GPUs and we can actually simulate them?
You want to comment on that, Peter?
GPU expert. If I knew what GPU stood for, then I'd answer it. But I was just going to answer number one. It's definitively no, I think, is the answer, but we do our best. But I did have a couple of comments that we've heard many times this morning, that a quarter degree GM kills the eddy energy. But there are two ways that I've seen in the past about how that can be reduced. One is an anisotropic form of GM, which I worked on a long time ago. But more recently, and maybe easier to implement, is the one by the Hong Kong group, where they say they should average over either time or space the density gradients, so that GM is then working on much, much weaker density gradients than you get in instantaneous mesoscale eddies. So if you work on much weaker slopes, then the GM effect is strongly reduced. So the killing of the eddy energy can be reduced. So
I'm wondering whether any groups are wondering whether to implement that sort of thing.
So we have been, this is Bob Hallberg, we have been talking about these ideas, and we were really impressed with the idea of using spatial filtering, but the original implementations were in a Z-coordinate model, and so you're averaging in Z, okay, that's well defined. If you're not, figuring out exactly what the right kind of averaging of to get the large scales is something that I think needs a fair bit of thought. And we don't have a good answer to that, especially if you start averaging and you have complicated topography and you add lots of complications. It's a good idea, but it's one where the devils are in some of the details.
Any comments or further questions? Yan?
So I'm from the Hong Kong group, but I didn't lead that construction. Julian did. So basically, that's a very decent idea. But then there's also other issues also documented in the paper. It's not a perfect splitting. So basically, it's using the large-scale information to construct the GM, but that GM must still work on the total buoyancy field, which means, for example, if you're approaching high latitude or boundary current systems, there's still a strong variance of the mean buoyancy field. Still, I'm anticipating dissipating a lot of buoyancy variance. And also tested to be a little overly dissipative, overstanding meanders in the Thousand Ocean. So that's an issue. The other related issue is the current filter mostly isotropic in horizontal. So, but we know that even the ocean mean circulation, they are not isotropic depending on the location. So last night we were discussing with Gustavo and Dhruv, there any way to implement anisotropic filters online? Yeah.
So a direct response to that is the internal wave community are using Lagrangian filters, which is one thing to consider. So I would like to say, I mean, I think it's great to talk about what didn't work, but it's also the first attempt at this, and we know it's going to take many iterations. So I'm actually inspired to think that this is a really good idea. And the reason I think it's really good is because it connects through to a lot of the work we've done in the last decade about understanding from the turbulence community, I think, the role of filtering. We're not, we always have always thought of the suboceanic mantle as exactly subgrid scale, but in reality, as we've learned from the French and so on, that there is an effective resolution and it's a lot larger than the grid scale. And we actually have there's a very imprecise but smoothish transition between what's resolved and what we need to parameterize. And so I think that's what I like about the idea, is actually directly going after that. And I think we can build on this, and there's hope.
Someone has related.
Does anybody want to comment on these last two comments? If not, go ahead.
Yeah, just circling back to Paul's point, I think that as we go to high resolution, there's more we discover than mesoscale eddies and how mesoscale eddies interact with bathymetry and topography. So I think in answer to your question, I would say, unfortunately, I think we have to keep working on our parameterizations for low resolution models and move to GPUs for high resolution models. Yeah.
I just want to ask another question, which has already been asked by Steve in another meeting before. It's about the relative importance of numerical scheme and parameterization. So currently we're in eddy permitting resolution. So actually both the numerical scheme and the lack of scale resolution are affecting the large scale circulations. So we are mostly working on the MS scale parameterization. We are hoping the parameterization to fix all those bias. But there are also groups like Simone. They use a high order numerical scheme, which can also achieve a much better effective resolution, which can also help you reduce the bias. I'm wondering, what's the comment on the relative importance between parameterization and the numerical scheme?
I heard you two are going to implement high order on Thursday.
Yeah, I want to comment on this. I think it's nice to have a higher effective resolution, but probably at a quarter of a degree, what we see is that still there's a lot of energy that we're lacking. So we really need parameterization in that regime, I think. I don't know if using DG or some much more elaborate scheme, you can really get to much higher effective resolutions. But I guess in the Eddy permitting regime, you're really not resolving the deformation radius. So you gotta inject that energy somehow.
Hi, yeah, this is Spencer Jones. I guess I'm kind of building on some things that Andrew and Andy said earlier. Like, I think one thing that I find when I watch the talks, I'm like, oh, you've put in a whole lot of work, but it's hard to figure out in what way is the parameterization deficient, right? And so, like, I wonder if there's a way. So splitting down into these components, the IFS, the Reynolds stress, the isopignal stirring, like which of these three things maybe is not working, and also comparing to perhaps like more like echo derived or some kind of inversion method ideas about what those values should be might be a way forward to. Because otherwise you just get a whole bunch of parameterizations and you don't know what's wrong with them other than, oh, it looks different. And yeah, I think that's a place where I mean, yeah, I'd be interested to hear what people think we can do.
Andrew?
I'll partly. So I'll partly respond to that. I mean, I think that it's interesting to think about this because, like, I think there is an implied assumption, I think, in all of this, right, that if we improve the representation of mesoscale eddies, like the form stress or whatever, right, that this will lead to a direct improvement in a complex quarter degree model in a complex coupled model system where we think about biogeochemistry, right, and like we care about carbon uptake and stuff like that. And I think this is one of the underlying hypotheses of the community, right, that as we increase complexity of our models become better. I think there is the legitimate question in the hierarchy of models, and not just thinking about hierarchy of complexity of resolution, but hierarchies of complexity of models, which asks this question, like, what is the minimum complexity model needed to answer the questions of the climate community? And I think that that's where it becomes a real question about, are we fixating on getting the answer right in a very like specific box that does not necessarily project onto the large scale and the bigger questions that we use these climate models for?
Okay, we still have 5 minutes left for discussion. Steve?
Yeah, Stephen Griffiths. Yeah, that provoked me a bit, Andrew. Thanks. I think that we do know that the parameterizations have an effect on climate heat uptake and carbon. I mean, we've done generation or so of tests, and they are the parameterization, the sensitivity of big climate questions are there and pretty well documented. I mean, Jet McWilliams eddy effect affects the rate at which heat is uptaken, and the drift in the models and so forth. They affect a lot of things. So that's just a comment about that. I think that these things have relevance. And now how to parameterize them is the question. Ian said something that I really also thought I've been pondering about, because I really think it's everything he said about the when you were talking about the direct cascade and the homogeneous isotropic turbulence, and then the geophysical problem, the distinction between the two is I totally agree with, but I'm not. I think of it opposite to the to what you were suggesting, in that parameterization problem in the geophysical community, or the geophysical problem, is complex because of the boundary conditions or the things that are molding the turbulence. And if you can get, and I think you said this, but I just wanted to reemphasize it. If you can get that piece of it, like what Jan's doing with the topography, if you give that information to the parameterization, that's something that's more than the 3D isotropic turbulence people have. They have nothing except turbulence. We have something that provides order to our turbulence. And if we can make use of that order somehow, that I think is what we're trying to do. We know beta, we know topography, we know F, and those are givens that the isotropic turbulence community doesn't have. They just have stuff whirling around. And so maybe that's turning the problem on the other side and saying we may have an easier problem, although it's complex because we see a lot more structure. Anyway, that's just some thoughts.
Which one, Peter and Bob?
So at the CSM workshop this summer, there were several to many talks which showed that simulations using 1/10 of a degree ocean and 1/4 degree atmosphere really improved the climate. So it's, I think, absolutely clear that the mesoscale eddies, which are then resolved, are really important in improving the climate. Still, the disadvantage of those is there's a very relatively few of those integrations because of the computer time involved. But I think it is definitely clear from that improving mesoscale eddy parameterizations is important for the climate.
So Eric wants to respond.
But here, Peter, you make the assumption that going to 1/10 of a degree, the improvement is entirely due to mesoscale eddies and not the improvement topography or other aspects. So that's, I think I question a little bit sometimes some of the parameterization, the way they're derived, if you use identical configuration without changing any of the topography, other things.
Well, they go together, but I strongly believe that in 1/10 of a degree, the biggest effects are mesoscale eddies. So.
So I disagree. Actually, in our 10th degree model, the biggest improvement in the model drift and getting the right climate is that we get bottom water right, and that's not because of eddies. So I agree that eddies are important, but they're not the only thing that we improve by going to 1/10, and we need all of those things.
So three thoughts now on what are the main barriers. One, there is no resolution at which we resolve all the eddies. Even at 1/10 of a degree, there are still smaller eddies in some regions. And so the challenge of parameterization persists. Number two, climate models are inherently an exercise in compensating errors. And anytime you fix one thing, you undo the compensation of some other error in a tuned climate model. And so things always get worse at first. And so spotting the parameterizations that are actually making things look better requires a little bit more subtle analysis than just looking at broad metrics like RMS sea surface temperature errors or things like that. The third challenge that we've run into again and again is that things that work really well in idealized problems have this nasty way of interacting with non-eddying stuff, mean structures, at comparable scales in ways that get amplified and make things look unambiguously worse, even though you might be capturing some of the eddy effects. And that's just the challenge of the complicated geometry and the complicated dynamics of the ocean.
Okay, can we move on now?
Can we just thank all the speakers for the morning before?
Okay, so we're going to move on to the vertical mixing parameterization session. And we have 4 talks. And yes, Bob is the first talk. Applying implicit energetics ideas to simulate full water column ocean mixing. And then the second talk is going to be given by Florian Lemarie, because I guess it's your student, correct? Couldn't make it? So, and then after lunch, I guess the 4th talk is going to be remote. Now, for the speakers, at the 15-minute point, I'm going to say hello. And then at 17 minutes, that's when I'm going to say we need to stop so we can have some questions. Okay.
Great. Thank you very much. So today I'm going to present some partially completed work that presents the secrets in the sauce of what we've done in boundary layer mixing, but it's also something that we think can apply very broadly to three-dimensional turbulent mixing in a stratified ocean in a way that dramatically improves the numerical robustness and the stability of the system in a way that we think could carry over to a wide variety of different parameterizations. Now, pardon? It's fallen asleep. Okay. So the basic idea is pretty simple. Mixing in stratified fluid takes energy. We know that the sources of energy and the conditions in the ocean will be changing in an evolving climate, most prominently, including changes in the external forcing, the wind forcing, the internal and external tides, and others. And moreover, the evolving stratification is going to change the turbulent energetics. It's going to change where the energy goes and the efficiency with which it breaks. And so as a kind of a broad principle, one of the things we are trying to do with our next generation of climate models at GFDL is replace a whole set of fixed diffusivities with energetically based diffusivities where you can tie it back to physical processes. And I'm aware of a number of other groups around the world who are attempting to move in a similar direction. In our case, though, what we're doing that may be a little bit different is that we are doing this using an integrated implicit energetics approach. So this is making the transition here between physics and numerics in a way that hopefully will make sense in the end. So many of you have seen or studied or used parameterizations of mixing that might be rather elaborate. In many cases, you need two equations, something giving you an energy budget, and then some other equation for a length scale or a decay rate or something else. But in a lot of cases, what they'll boil down to is this Osborne relationship down here in the red box that I'm not even going to attempt to point to with this pointer, which basically says that when you're mixing in stratified fluid, if you know how much energy you're putting in and you have an estimate of essentially the efficiency, Flux-Richardson number based related efficiency, the stratification can give you a diffusivity, then you apply this diffusivity. And so you basically, if you have a theory for how much energy there is, you can translate that into a diffusivity. And that works really well in a number of cases. It's been used observationally to infer estimates from Argo of the average diffusivity over broad regions of the ocean, looking at microstructured turbulence. And again, this is using this Osborne relationship between dissipation and diffusivities. We've also applied this in parameterizations of high mode tide-driven mixing. For instance, here we have a map of the generation of high mode mixing based on the barotropic tidal amplitude and the topographic roughness and the bottom stratification. The bottom stratification is something that can co-evolve with the model, and this is actually done in a variety of climate models. This is a map of the energy, and then you may have some theory or some empirical description of the vertical structure with which that energy is deposited in the ocean, and then some efficiencies gives you a dissipation rate, and from that dissipation rate, you get a diffusivity. Great. This works really well, except when it doesn't. And the reason why it doesn't work really well is that there are places in the ocean where the stratification can get weak, where the stratification can change significantly over the course of even a model time step. And in those cases, the estimate of an infinite diffusivity really is not very good. So rather than sticking with the Osborne relationship, we have a new implicit energetics approach, which basically says that the turbulent kinetic energy that you're supplying has to support the potential energy changes throughout the entire water column over a time step. In the limit where the time step goes to 0, the stratification can't change. These essentially are the same. However, by rephrasing it in this way, it tells us how to work the energetics in an essentially exact way for implicit mixing over a finite time step in a way that actually works really well in places like boundary layers where the stratification is effectively so small that it's not n squared you're looking at, it's the evolution of the density in the water column itself. The first key step in deriving this is one that's pretty simple. It's basically saying that you look at the change in the potential energy of the water column, and you've all seen this in your first physics course. And the thing, though, that is worth noting here is that if you are doing this in a non-Boosanesque coordinate, making no approximations, that you can change this from an integral equation where as you mix, the sea surface goes up and down, and so you have changes both in the boundary condition and the interior. In a non-Boosanesque framework, you can recast this as an integral over the range of pressure in your water column, hydrostatic pressure, and that does not change as a result of mixing. And it is an expression that is linear in the specific volume. Here, R is specific volume, 1 over rho. And this is all exact. The derivation is all here. I'm not going to go through this. You can check the slides and check my math later. But the beautiful thing about this is linear in specific volume. It has fixed bounds of integration and pressure. Great. Moreover, the change in the potential energy of the column due to the change in the mixing at an interface is something that you can then calculate pretty straightforwardly. And you can relate that to mixing throughout the entire water column if you have diffusivities elsewhere in the water column where you've already paid for their energetic consequences. And what we'll do with this is we'll say, okay, if the potential energy of the water column is increasing, that's a sink of energy. If the potential energy of the water column is being released, that happens in the case of convection, that's mostly a release of potential energy. It can drive further entrainment by some fraction, and empirically we've determined that to be something of order maybe 7%. You can quibble about the number, but it's an efficiency that's less than 1, with one small caveat, and that is when you mix due to the nonlinear equation of state, the water column as a whole contracts. It's just due to the curvature of the equation of state. The energy that's released from contracting the whole water column isn't available to drive more mixing locally. It mostly radiates as external gravity waves. And so we just say that goes away. And so we're separating that out. So this piece is pretty simple. The next piece is to realize that mixing is something that we do conservatively for potential temperature and salinity. And if we linearize the thermal expansion coefficient, the haline contraction coefficients, then this also turns into a linear expression for the change in the temperature and salinity that then relate to the change in density. And we can combine all of these together by writing our tridiagonal solver for the mixing in the right way. And the right way here is avoid subtraction in the denominator. We get some really robust expressions. Usually you write a tridiagonal solver moving from the top down or the bottom up. You can also do it working inward first and then from the interior out. And this final form is the key piece that we're putting all together as a third linear piece of this puzzle, where we can describe the entire changes in the potential energy of the water column due to a fairly compact local expression. The details are here. You can look at the slides later. I'm not going through them in detail, but we can combine these 3 linear equations to describe, get this expression highlighted in white, which is the change in potential energy from the entire water column due to a change in the diffusivity at a particular interface. Now, this is nonlinear in the diffusivity, but it's a relatively simple expression, and it's relatively easy to invert. There are a couple of things to note here. First, the buoyancy frequency, the thing that was going to 0, hard to estimate how it would evolve, doesn't appear anywhere in these expressions. They're essentially exact. The only approximations here, finite volume form of the equations, we're making the hydrostatic balance, and the thermal expansion and haline contraction coefficients of the layer don't change very much over a time step. Apart from that, this is all exact. So this is all kind of kinematics. Now, you can take these expressions and apply it to a relatively simple case where you're mixing between 2 layers. And the thing that's worth noting here is that there is a finite maximum change in potential energy due to mixing at a particular location. Once you've done mixing, further stirring doesn't change anything. And this is something that you can work out straightforwardly in a 2-layer model. So there is a limit where you have homogenized things. There's a finite amount of potential energy change that you can apply locally. If it weren't for this, you could just say, give me the energy, and you have a one-to-one mapping onto the diffusivity, but that could give you an infinite diffusivity from these expressions. And so what we need to go with this is some other ideas of what the maximum mixing might be, a maximum diffusivity. And a typical way to do this might be to use some kind of a mixing length sort of argument where you say that the diffusivity is a magnitude of your turbulent velocity times a length. This has been something that people have been doing for many years. This is at the basis of, for instance, parts of KPP, parts of, this is law of the wall. This is stuff that has been demonstrated many times in turbulence. If you're working in a boundary layer, people have thought about these ideas a lot. There's a lot to work on. If you're working in the interior ocean, that's where things get a little bit fuzzier, and that's where I'm actually a bit stuck on how to apply this universally. But there are several considerations here. First off, the vertical gradient of the length scale has to be less than 1. The eddies can't overlap each other. And this is at the heart of, for instance, law of the wall scaling. We know that this length scale is something that's going to go to 0 at a solid boundary, or maybe to a wave amplitude in a wavy boundary, or it goes to 0 when the stratification is sufficiently strong. And then finally, you can use the energetics of a turbulent kinetic energy flux to estimate a turbulent velocity, or you could use a stress, so a friction velocity. And so these are all things that are kind of elements of what you might use in general. You also might want to take into account that turbulence can auto-diffuse itself. So even if you apply energy in some place, within a time step, if the mixing is strong enough that things can spread themselves out. The details on all of this with the peak diffusivity, they all depend on the mixing process. But the beautiful thing about the energetics is it's essentially an exact calculation. So we're looking at applying it to a whole bunch of different processes in the ocean. Today, I will very briefly discuss 3. How many are doing? I don't know what time I started. I'm at 12 minutes. Perfect. Okay. Yeah. That clock said I was out of time, but I started late. So one example here is our energetics planetary boundary layer, which combines the energetics, this exact energy calculation, with a lot of thinking about the distances and the vertical viscosities that could be derived, for instance, from papers like KPP with mixing link arguments. The beautiful thing about this is, although we're calculating these length scales, the thing that really controls the mixing is this exact calculation of the changes in energy. And this gives us something that is remarkably insensitive to vertical resolution or time step in the surface boundary layer. So these are 3 different cases just taken straight out of the box. And as we change from a 1 meter resolution to a 20 meter resolution, and as we change from a time step of something very short to something of relatively long, the fact that it's the potential energy budget that's closing means that the potential energy associated with the homogenization of a mixed layer is a robust diagnostic across length scales. And in applying these ideas, this is work that Brandon Reichel has done, we have found that in going across successive generations of GFDL climate models where we changed the boundary layer scheme to use this idea, we got systematic improvements in the parameterized boundary layer properties. We've now flipped this upside down and we're applying this as a bottom boundary layer flux. And this works very well in that context as well, in that we're exploiting the fact that the amount of mixing is very well constrained. It's insensitive to the resolution. Even if the resolution is very coarse, the model compensates for itself by regulating it down so there's only a finite amount of mixing over a very large distance, so that the energy change is really what's constraining the system. And then the final application here, and this is one that's in progress, is looking at stratified shear mixing. So in the case, for instance, of an overflow, in areas where you have a small Richardson number, the mechanical energy is able to drive overturns. And in this case, this is a 2-equation closure that we've been using some time due to some work by Laura Jackson et al. But there's a key term here, this circled term on the top. This is a vertical buoyancy flux. We are re-implementing this so that this vertical buoyancy flux is now going to be using the exact implicit energetics. Our expectation is that it will give something physically similar, but the iterations will converge much, much more quickly and to the right answer. So this has been a whirlwind tour. The key points here are that there is this one piece that can be applied very generally to any energetically based mixing parameterization, in that we have essentially a closed expression. It's efficient enough that you can solve for it one layer at a time, adjust everything above and everything below without having to retraverse the water column. So it's an order NZ calculation. It's not NZ squared as it might be at first thought. And so it's effective enough for use in climate models. And we are actively exploring the use of this idea across a wide variety of different energetically constrained mixing processes in MOM6. So the bottom boundary layer mixing is something that's available now, following on the success of the surface boundary layer EPBL. We're working on this full column energetics. They're the estimate of the length scale when you're far from a boundary and far from vertical structure is the thing that's holding it up. But we also think that this is something that will translate very naturally into an improved, as in more rapidly converging version of the Jackson stratified shear mixing parameterization. And I think it's something that could carry over into a wide variety of problems. The one last thing I'm going to say is this lends itself very well to combinations with machine learning. This is an energetic framework that's solid. There are lots of details of the shapes and the length scales and efficiencies, and that's one where machine learning within this context can be used very effectively to come up with even better parameterizations. And you'll hear a little bit more about this from Aakash Sane after lunch. So.
Okay, questions, please.
Yeah, Mats Benson, North Norway. So it is very nice that it is energetically consistent. I was thinking about numerical mixing. Can you use this scheme to compensate? For example, AL regridding and remapping, then you can compute a potential energy change in that process. Could that be subtracted from the energy input there so you can?
Huh, that's a good thought. I hadn't thought of that. Maybe. The challenge is you would like to know that your numerical mixing is responding in a similar way. If there's too much mixing, you can't unmix. You don't know how to unmix. This is all predicated on the idea that you can use a positive definite diffusivity. If it's small enough, you probably could do it, especially if you know where in the water column that effective excess mixing is localized. So I believe Bill Large has a question.
Yeah, it has to do with predication. I mean, eddy diffusivity is a property maybe of the flow, but it certainly isn't of the fluid, as opposed to molecular. There's also mixing of momentum, which you haven't mentioned. So how predicated is all this on the fact that diffusivity is a good concept? Eddy diffusivity.
And specifically, there are some well-known papers that point out that the buoyancy fluxes in the boundary layer are actually counter to the large-scale gradient with the non-local part of KPP, for instance. If you have some other way of describing the fluxes and then capture the energetics, you can apply them in combination. You can have an explicit upgradient flux. This is saying the piece that you're doing is downgradient. I don't know how to combine the other things. The nice thing about this is you can combine, there's some nice properties in terms of the dissipation of variance and the increase of energy from the mixing using downgradient dissipation, and the numerics work together in a way that even though the expressions there were admittedly horribly complicated, it's linear and robust. And so you would break it down into pieces. If you thought you had a description of some other piece, I don't see why you couldn't combine them. momentum is a challenge because kinetic energy is nonlinear. We apply implicit mixing of momentum. In this case, there is a kinetic energy equation here. This is the stratified shear mixing. The dominant source term is the kinetic energy. We probably are going to have to apply something iterative or explicit. We can't do the whole water column all at once. But the fact that you're doing the whole water column all at once for a dominant sink term here should help us to converge much more quickly in the iterations.
I think we should move on. Okay, thank you very much. Okay. So the title of the next talk is Derivation of an Energetically Consistent Eddy Diffusivity Mass Flux Scheme for Oceanic Convection.
Okay, thank you. So I give this talk on behalf of my student Manolis Perrot, who couldn't make it here. Part of his work is about the application of the EDMF concept to oceanic convection. So this is funded by the French Navy, the CHOM, and the Mathematical Institute for Planet Earth. So the basic objective of this work was to try to derive a parameterization for convection from first principle and to be able to really have access to explicitly to the assumption we made during the derivation of the parameterization. And in the end, the expectation is to achieve a resolution-aware parameterization and a consistent energy budget to have the proper transfer between your dynamical core and your physical parameterization. And so the case study here is a parameterization of vertical turbulent fluxes in the boundary layer under a combined effect of local turbulence and convective plumes. So why this case is interesting is because it has been known for almost 60 years that actually the eddy diffusivity approach fails in this case. And because the transport by dense plumes is not directly related to the local gradients. So you can see it from a simulation if you want to be convinced. But so in this case, what are the alternatives in practice? So what has been widely used in the oceanic context is the use of what I call a gradient correction factor or counter gradient term, whatever. You have an additional degrees of freedom, this gamma term in pink, that allows you more or less to give a form to your flux that is independent, that could be independent to the sign of the, independent to the local gradient. Another possibility is to use like a sorting algorithm where you just rearrange the unstable portions of your density profile. And another possibility, which is, I think, quite popular in the atmospheric community and less in the oceanic community, is to do like coherent structures modeling. So it encompasses different approaches. So the complicated approach is a multi-fluid modeling. So it has been proposed by, for example, by John Suburn or by Tan in the concept, in the framework of the climate project. And the, I think, easiest way to go is the mass flux scheme, are the mass flux schemes. So there is a huge literature in the atmosphere, much less in the ocean, and I call it a proof of concept by Giordani for the moment that is already existing. So the idea is really to combine eddy diffusivity to represent small-scale isotropic turbulence with what we call a mass flux to take into account the contribution from coherent structures. So the outline here, I will go from the two-fluid modeling framework to mass flux schemes and to detail all the assumptions we have to make, actually. And then I will show that we should not really consider development of the two components completely separately, as it is sometimes done, because the two components are energetically connected. I will very briefly mention the practical implementation and show some numerical experiments. So really the basic principle is now if you take any quantity, so phi bar here, in a finite volume sense, in your model, you have two contributions to this average, one from the coherent structure, one from what we call the environment. So the environment is characterized by local turbulence. And you allow between those two, more or less, fluids, an exchange of mass through entrainment and detrainment. So in the rest of the talk, I will note AP and AE, the fractional areas for each fluid. I have W vertical velocities and phi, any advective field. So it could be like UV, theta S, but it could be any biochemical tracer if you want. Now, if you apply this decomposition to your turbulent fluxes, you end up with 4 components. And for each subdomain, actually, you have the contribution from coherent structures and the contribution from subdomain turbulence. So at this point, you can consider that, okay, for the local turbulence, you just consider a standard eddy diffusivity term. And the 2 contributions from coherent structure can be gathered as just one term. So this is the term I show here for coherent structures. And I just do the assumption that the W bar is negligibly small. So the average vertical velocity in practice. So at this point, we still need to specify all the plume quantities, the vertical velocity, the area, and this phi p quantity. So in this case, this is where you start having, you could not make any assumption, but it's better to do a few assumptions to have something easier. So you just start from your standard equation, d phi dt equals sources, for example. You apply explicitly your averaging operator over the plumes. And the first assumption we make at this point is what we call the steady plume hypothesis. It means that you neglect the time derivative in front of the vertical advection term. So we did a scaling for that, and it is something that is very well satisfied, and we can really, it does not compromise the scale selectivity, scale awareness at this point. What is more important is that most of the mass flux schemes, they do what is called the small area limit, meaning that they consider that the size, the fractional area occupied by the plumes is very small compared to the whole area of your grid cell. And it's easy to understand that in this case, you cannot really go to finer and finer scale with that, because at some point, the area occupied by the plume can be significant compared to the area of the cell. And I don't know why, really, there is a belief in the literature that to relax the small area limit, you have to reintroduce the time derivative in your equations, but it's clearly not justified. So you can, our point is first that you can really relax this small area limit without any additional complications. I just summarize here the derivation, but you just have this parameter alpha. If you take it to 1, you are in the small area limit. So it's a standard mass flux scheme you will find in any atmospheric model. But you just have to replace it by 1 over 1 minus AP. And in this case, you don't have any limitation on the size of the size of the plume occupied by the plume. So in the end, what you obtain is a parameterization. You have to solve a few nonlinear ODEs. So those are initial value problems. You start from the surface and you just propagate the information downward. It's relatively cheap to compute. Maybe what is less cheap sometimes is you have to apply the equation of state on the plume quantities. So depending on the complexity of your equation of state, it can be costly. So all what I said is summarized in a paper that is under review. So there is a version available already. And in this paper, we really consider a more general framework, which considers dry convection and convection in the ocean. And by considering actually a more complete, like Boussinesque and elastic system of equations. So that it can be, all those concepts can be applied also to dry convection in the atmosphere. Now, if we go to the eddy diffusivity part, I mentioned at the beginning that we would like to have some kind of energetic consistency. So what is natural in this case is to use TKA-based eddy closure, eddy diffusion closure. So in our case, we use in practice the NEMO closure. So it's a one equation turbulence model. And what is important in this case, as soon as you have this prognostic equation for TKE, is the fact that the mass flux term is going to lead to energy exchanges. So you will have a coupling between ED and MF. They are not independent, and this is through this TKE equation that you can couple the two properly. So you just need to do some horizontally average energy budget to see it. So this is the usual picture here. So you have the resolved kinetic energy, potential energy, and TKE. You have exchanges. Specifically from resolved KE to TKE, you have the buoyancy, the shear production term in your TKE equation, but you need to add an additional component due to the mass flux. And same thing here for the exchange with, in terms of potential energy with the TKE value. And so I will show the equation you obtain in the end actually after. And of course, you have also to be careful with the boundary condition, because sometimes you have some form of mass fluxes, mass flux scheme with non-zero surface boundary condition, and in this case, you have to be careful to remove this component from what you impose for your eddy diffusivity to be consistent in terms of energy. So in the end, what you obtain for your TKE equation, you have two additional terms related to the mass flux. And on top of that, you have also to think about, you have additional terms for the turbulent transport of TKE. And those terms are super important to really redistribute on the vertical your turbulent kinetic energy. And what is interesting is that if you look at the literature in the atmospheric community, so you have a paper by Vitek where the second term is proposed, more based on intuitions to fit like LES simulation. And in Hahn and Bretterton, you have only the first term, so the mass flux on the TKE. So what we show is that you really need all those ingredients at the same time, and there is no ambiguity about that because you just derive things from first principle. So in the end, is it really useful? So first, I think it is super useful for sanity check because in this case, you can obtain closed energy budget in the end between resolve, if you consider really resolve and subgrid scales. And in this case, we adjust what I showed before, not here, is that it's not very useful in the ocean, but it's useful in the atmosphere, but also we transfer the dissipation of TKE in terms of internal energy. So you should be able, in this case, this is like a sanity check to completely close your energy budget in your single column model. And what is, I think, more important also is the fact that really by doing it, you end up with TKE profiles that are much better compared to LES simulation with this new formulation, actually. And this is something that is very robust, whatever the test case you use. So for the practical implementation, I will be very brief. In practice, of course, to be able to close this energy budget at the discrete level, you need to pay attention to how you discretize things. And this is the reason why we just extended the Burchard 2002 concept, actually. So it was applied only to eddy diffusivity. So the concept here is simple. It's just to rederive at the discrete level what I showed at the continuous level. And you end up with a unique way to discretize all the source term in your TKE equation. And also what we have done, actually, is also to adapt more or less this approach also, not only when you have loss of buoyancy at the surface, but whenever in your water column you have like an unstable profile, it can be applied. So there is a second part of the paper I mentioned earlier, actually, about more the implementation and comparison with the LES simulation. And just when you apply it, you have two choices, actually, when you apply it in practice. Either you just put the mass flux term in your tridimensional solver with the eddy diffusivity. So it means that you will treat the two terms at the same time. Here we prefer to have like a boundary layer, what we call a boundary layer Zen convection strategy, which allows a better phasing between the different quantities. So I don't go into the details. And of course, what is important is that you have to finish your time step with TKE because you need to be aware of all the energy exchanges that happen during your time step. So I will go on for numerical experiment. How much time do we? Well, easy. Okay, sorry. So I will take the time to discuss the things here. So to validate more or less our approach, and we started with Bruno Doramble actually in Grenoble to gather more or less LES simulation results from LES simulation, and we asked even Luke, who is somewhere here, sorry, who sent us a few examples also with NCAR LES outputs. This is completely on purpose that we use very different tools for the moment to do this actually, and we will add additional tools in the next few months. It's really to be able to have like statistics about the model errors, or maybe at least to check that there is consistency between the different numerical tools. And because when you will do the calibration, we would like to make sure that, okay, if you consider that your LES simulation is really the truth without any error, we want to make sure this is really the case. And also to validate, so I will just discuss the two cases in red here. And we also did like a realistic case from the Giordani paper that is like an intense convective situation in the Mediterranean Sea, for which we have a lot of observations. So here I just show the very simple free convection case. I add to the discussion this gray line here, it's called ED plus EVD. So this is a standard way to go in NEMO, for example, where you just use what is called enhanced vertical diffusion. So where you have an unstable profile, you just mix a lot. And so this in black, you have the LES results. So for temperature, turbulent flux, TKE, and turbulent transport of TKE. So in red, we have our new scheme, this is DMF energy. So as expected, you have really, as I said, much better agreement in terms of TKE and in terms of turbulent transport of TKE. Otherwise, there is no, the effect on the mean quantities is not large because we have convective plumes. So really the turbulent transport, the turbulent flux is dominated by the coherent structures, and the eddy diffusivity part has a very minor impact on the things. And now if I compare also to the, so I use the KPP CV mix with the non-local term. Here, it's not, the point is really not to make any comparison. It's more like to look at the figure on the right here, where we just saw the eddy diffusivity part of the turbulent flux and the non-local part of the turbulent flux. Because at the beginning of this work, we wanted to make like a link between this gamma in the non-local term in KPP and our mass flux quantities. And actually, this link, you cannot really make it because really fundamentally, the two approaches are completely different. So when you try to model the coherent structures, your flux is really explained by the non-local part, more or less, and your eddy diffusivity is only active really just near the surface is the boundary layer, otherwise it's almost zero. And in the KPP with non-local term approach, you have more like self-similar functions. Okay, thank you. Self-similar functions, more or less to compensate probably. So your eddy diffusivity term is non-negligible in this case, for example. And same thing if you add a wind, but you have more or less the same conclusion also. So I have to say that here we applied the mass flux term also to momentum. And again, if we look at the comparison with KPP does really super well here without any tuning in this case. And in the KPP CV mix implementation I have, there is no non-local term on the momentum. So this may explain this difference in terms of for the velocity here. Very quickly, so this is the realistic case I mentioned. So this is a case observed in the northwestern Mediterranean Sea during the winter 2013. And you see that for almost 3 weeks consecutively, you had a negative buoyancy flux at the surface. And even the convective plumes, they just reach the bottom of the ocean at 2,500 meters. So this is what you get at February 9. Actually, you get just a straight line. So here in red, I show the observations. And so with this EDMF scheme, we are able to reproduce mostly what we see here and what is. So I show here, for example, to be the mixed layer depth. In black, this is from the numerical simulation, and in red, this is from observations. And we do a better job than, for example, the standard NEMO or CROCO way to parameterize things. Just to summarize, actually, the idea is to develop some form of eddy diffusivity mass flux parameterization for convection. You have those two terms now to define your turbulent flux. This is a PDA-based ready derivation with explicit assumptions. And we can have fully consistent subwind and reserve energy budget in a single column framework. And it has been evaluated against LES simulations. So there are 2 papers, as I mentioned, under review and available already. Now the work in progress is so the sensitivity analysis is done actually. So we have 6 parameters in this closure, but 4 of them, we can take values from the atmosphere, for example, or whatever, it does not really matter. You can rely on mostly on the calibration that has been done in the atmospheric community for most of the parameters. But anyway, what is interesting also is that so Bruno Oderambe is leading a project in Grenoble to use also the Coriolis rotating platform to revisit like the Cato Philippe case, for example, with rotation, to have like some convective cases also. So it could be interesting to use those data to calibrate the. Sorry.
Stop now.
So it's okay. I can stop here. Sorry.
So thank you very much, and also to Manolis. And we've got time for one very quick question.
Very quick one. Yeah, really nice. Have you done resolution and time step sensitivity?
Yes, we show it in the paper, but yeah, I don't know. For the TKA scheme in NEMO, for example, is super robust to special. The ED part for sure is robust, and even the mass. So in the paper, we show a figure. We even go to very low resolution in to 50-meter resolution in the vertical, I think something like that. No, it's from what I can see, it's relatively robust to that. But if you want more precise measure, in the I think in the appendix of the second paper, we have a figure to show it.
Okay, so it's lunchtime. See you all back at 2. Thanks.
Fine. Is this fine?
Yeah. So I might recommend putting it.
And okay. So when should I start?
As soon as you're ready, we'll start.
I'm good.
Okay, well, I think we'll get started. Welcome back, everyone. Thank you. Okay, so we're going to start this afternoon's part of the session with Aakash Sane talking about parameterizing vertical turbulent mixing coefficients for the ocean surface boundary layer using machine learning. Thank you.
Thanks for the introduction. So I'm Aakash Sane. I'm a postdoc at Princeton and GFDL. And the short title of my talk is Modeling Vertical Diffusivity for Ocean Surface Boundary Layer using Machine Learning. And here are some key points of my presentation. So in short, I have taken a neural network approach as a first step to bring in diffusivity from a higher moment closure into a first order closure, the EPBL closure as described by Bob Hallberg. And the control scheme had showed some bias in the tropical regions, and this bias is shown over here in a blue patch, and it shows that the mixed layer depths were deeper than Argo observations. With the neural network based diffusivity, that bias reduced significantly, and that's what we see in the second image. And this is model versus observation comparison. And the third point is that I have some equations which approximate what the networks were doing. And it showed a similar skill when we ran this OMDP style model. But the equations also allow us to interpret what the networks are doing, and it leads to finding some potential deficiency in the baseline scheme. So these are the key points. So the challenge in vertical mixing is that we need to model the vertical turbulent flux, shown here as W prime T prime. And there are various ways to model this or parameterize this. And one parameterization or one way of modeling this is using the Eddy diffusivity model, which is given as some diffusivity kappa into the gradient of tracer. In this case, it's a temperature. And you can construct kappa using some arguments, some length, some velocity. And these terms can have some coefficients which could be ad hoc or tunable based on physics or based on empirical fitting. But they lead to uncertainty. And on the right, I'm showing a sensitivity study where I show that if you just change one parameter, which goes into the EPBL scheme, you can get a different evolution of the ocean, the total ocean heat content. The key thing is that the rate of warming is different for these three simulations. And they disagree by roughly 15% of 1 watt per meter square. So the uncertainty in these parameters is non-trivial. And it should be, and so this diffusivity should be constrained on better physics or better data to have more trust in our simulations. But then what's the challenge? So I'm just showing here what is the challenge that we face. I'm showing a plot of diffusivity profiles. Y-axis is sigma coordinate, x-axis is normalized diffusivity. And these lines show the structure of diffusivity from the top of the surface layer to the bottom of the boundary layer. The black dash dot line is a profile of diffusivity that we currently use in the EPBL scheme. And these brown and green lines are what we see, or what the diffusivity is in a better turbulence closure, relatively better than EPBL. And these brown and green colored lines have some information about the surface forcing. So the diffusivity responds, or the structure of diffusivity responds to the surface forcing. but the black dash dot line does not respond. And this is the brown and the green lines respond because they are from schemes which solve for some kind of turbulence quantity, such as turbulent kinetic energy or dissipation, length, etc. But the challenge is that they require a short time step, maybe 10 seconds, maybe 1 minute, maybe 2 minutes. So it is difficult to use these kind of schemes which have better diffusivity in a global model spanning long integration timescales. So we have to use schemes which have some approximation. They cannot solve TKE, but the schemes, but these kind of schemes which call as first order closures, we can use them with a time step of maybe 20-30 minutes. And this allows us to perform longer timescale simulations in an ensemble settings. And so this is what makes it possible to run, And what I will show is that this gap between these kind of better schemes and low order schemes can be closed with machine learning. And one goal is to, yes, bring in better physics, but the second goal is to understand whether this kind of complexity, does it really matter for long timescale simulations? Because we do not know that as of now. And so first approach I took was a neural network approach, where I modeled the diffusivity as a product of 3 terms. One is the G sigma, which is the shape function or the structure function. The second term is the boundary layer depth h, and the third term is the velocity scale. All of the vertical structure is in this first term G sigma, and h and v are scalars. And I use neural networks, so I had to generate some training data on which I can train them. And I used a package called as GOTM, which stands for General Ocean Turbulence Model. This is a 1D turbulence model where you can choose some kind of scheme. And I have chosen second moment closures such as K epsilon and GLS. And one reason why I chose this kind of schemes or this package is that because it's a 1D column, it's very cheap and fast to generate training data. These schemes are at least better than what we are using, that is the EPBL scheme, in terms of it resolving the turbulent kinetic energy and etc. And the diffusivity is a downgrade. It has the downgrade assumption, so it is stored as an output in the training data. So it's easy to just use it as it is from the NetStudio files. And so there are a lot of advantages to use this kind of intermediate complexity model rather than using larger simulations. So I took 2 neural networks I'm showing here. So this is the first network and this is the second network. And they take in inputs which are readily available in your ocean model, such as Coriolis parameters, surface friction velocity, etc. And one neural network gives me G sigma on a sigma grid. And the other neural network gives me velocity scale. And these terms have been diagnosed from the second moment closure. And once I have these 2 terms, I plug them back in over here to recover the diffusivity profile, except I do not touch H, because H comes from the implicit energetics formulation. And that H, because it's based on physics, it's not required to touch it. So all the ad hoc components are only in the first and the third term, and that's what the neural networks are replacing. And I coded this network in MOM6 mixing scheme, the EPBL mixing scheme. So it runs along with EPBL if you switch on a flag. And I'll show some results. And so here is a global simulation using MOM6 in a quarter degree configuration called OM4. And what I'm showing here in this red rectangle is the same plot that I showed on the first slide. Is that this is the summer mixed layer depth bias. And the first figure shows what is the bias in the control scheme without any enhancements. And the second image shows what happens when you improve the boundary layer physics using the neural networks. And because of better diffusivity, the bias is reduced. So we see that the neural network enhanced diffusivity leads to improved physics and bias reduction. But then the question is, can we interpret what the networks are doing? And we know what they're trained on, but can we understand what they have been doing in a GCM? And can we do that with equations? Short answer is yes. And can those equations replace the networks? Yes. And also show that we get a similar skill. So to go to the next step, I attacked the same term, which is G sigma and V. And first I targeted the structure or the shape function. Initially, a neural network was predicting this shape function, which goes from 0 to 1 in a sigma coordinate. So I found that we can approximate this using maybe some equation discovery techniques, but it was very challenging. And empirical fitting or equation discovery technique was not giving me the right solution if I was going for some higher order polynomials. But then I assumed that, or I realized that what the networks are doing is that the networks are predicting the location of where this maxima occurs. So I denote that by sigma max. So this is one thing that the networks are doing. And so if I capture that, that sigma max as a function of some terms, then that would give me where this peak lies. And the second thing that the networks are doing is getting the structure, the base of the boundary layer. And this is important for entrainment because entrainment happens over here. And so this is the second thing that the networks have been doing. So can I get these two terms? And maybe that would be enough. And this would be the leading order effect that should be captured. So for sigma m, I was able to do some empirical fitting. And the sigma m over here is a function of just two non-dimensional numbers. P1 is h divided by the Ekman depth, and P2 is h divided by Monod-Obukov depth. And using this model, I got a really good fit with the data. But when it came to the shape function at the base of the boundary, it was very challenging. So I went with some assumption, is that I assumed that the profile above sigma m is quadratic, and the profile below sigma m is cubic. This might not be what exactly the networks are doing, but it at least gives us some shape which is well behaved, and we can go forward with this and check what happens. So that is the first term, G sigma. And again, H is not changed because H comes from physics. Then the third term, velocity scale, is so for velocity scale, I tried the same approach. First, I tried symbolic regression techniques, which is a transformed form of machine learning. And I was able to get some expression for the surface heating and the neutral conditions, and it's very compact. And the left-hand side is V velocity scale by U star as a function of just one non-dimensional parameter given over here. And I was able to use a technique called as genetic programming. I will just show this video, small video, which shows what it is doing. So the green is data, and the algorithm is trying to find an expression which matches that data based on some loss function, I think L1 or L2, I forgot which one. And then it settles down at some expression which it thinks is good. And then I slightly change the coefficients as per the boundary conditions or etc. Or the extreme values. And so for the stable case, machine learning gave a really nice expression which you can easily read and understand. For surface cooling cases, this algorithm was not able to give me a nice and compact solution. But then I had to go with the method of looking at the data, trying to find some approximate fit, and then get some solution out of it. But overall, these two equations gave a really nice skill when compared with the true data. So the x-axis shows the true data, and the y-axis shows the prediction from the equations. And it's almost 1:1. So this is acceptable model for velocity. And so I got G sigma and V, which would have, which is what most likely the networks have been doing. And we can use these equations for G sigma and V to understand what the networks were doing. And this diffusivity that we get is very close to a second moment closure, but without any time stepping restrictions. There is still some uncertainty in terms of where the entrainment is happening. But anyway, so this is the same summer mixed setup result that I showed. But now I'm showing an additional plot which shows what happens when you run them with when you run the same experiment with equations. And we see a similar bias reduction compared with the control run. But it's not as good as the neural network, but maybe, but the advantage is that because it's equations, it is much cheaper than the neural network. So the neural networks have roughly 1,000 to 2,000 parameters which are automatically tuned. And that increases the computation cost, it's costly by about 5 to 10% of the GCM. But these equations which are approximating the neural networks, it's the same cost as running the baseline scheme. So this is great because now we have something which is which is something closer to what the networks were doing, but with the reduced cost. So this is great, but then the question is, why is this happening, and can the equations explain this, right? So to understand why we see what we see, I ran some single column experiments using MOM6. So I ran MOM6 in a single column by changing the surface heat flux at the and by changing the latitude and keeping the shear stress the same value in all these experiments. And I'm running the two schemes, the baseline scheme and the new equation based scheme. And what the top plot shows the amplitude of diffusivity at the end of the 10th day. And the x-axis is latitude. And what we see here is that if you just look at the amplitude of diffusivity, it was mixing, or the diffusivity was more than required if you think of this as the ground truth, right? This comes from second moment closure, which for our case is the ground truth. So it was more diffuse than required. And as you go for higher latitudes, the diffusivity was almost going towards similar values. And this could be pointed to the velocity scale, and you can see the same difference in the velocity scale. The equations gave a smaller value of velocity scale, and if you diagnose that from the baseline mixing scheme, it was having a larger value. And so this means that and this is for surface heating conditions. So for surface heating conditions at lower latitudes, the baseline EPBL was more diffuse than required. And this most probably or most likely explains why it was mixing more than required. And we can see that it's at lower latitudes, and this is for the summer mixed layer depth bias, which could correspond to surface heating. And so this explains what the networks or the equations are doing better than the baseline scheme. So this is great because we are able to understand what the networks have been doing and what the equations have been doing. But we can go one step ahead with the equations, because you could obtain the same plots with the neural network-based diffusivity. But if you go back and look at the equations, in the baseline EPBL scheme for surface heating, this velocity is it's a strong function of shear stress, but it doesn't have the surface buoyancy flux term active when we are in the surface heating conditions, or it's very weak. But the new diffusivity model for for the mixing coefficients has this term, and this heat flux tries to destroy turbulence, so it lowers the amplitude of diffusivity through the velocity scale. And we can pinpoint this using the new equations, which is what most probably the networks are doing. And so we can tie this in all together, saying that the equations allow us to interpret the networks, and they themselves can be used as a replacement to the networks as well as to the existing scheme. And we end up improving the physics as well as, fortunately, we see some bias reduction. So to conclude, complexity in higher order schemes can be captured and brought into first order closures because we want to assess the impacts on longer timescale simulations. Neural networks reduces biases in ocean-only experiments, and equations that replace neural networks, which are close to second moment closures, also reduce biases, but at a much lower cost. One more thing is that we are not breaking any conservation laws because we are in the framework of divergence of fluxes. So we end up satisfying conservation laws. Also, the physics of the original scheme have not been impacted because everything that has been done has been only done on the ad hoc or the tunable parameters. And the improved diffusivity has a lower amplitude for surface heating conditions, and this could be the reason why we see summer mixed layer depth, improvements in the summer mixed layer depth bias. So with this, I want to say thank you, and here's the paper that I published last year, and I'm writing the work that I presented today. So thank you.
All right, questions?
Thank you for the presentation. You're showing a lot of summer mixed layer depth bias. I was wondering, if I'm not mistaken, the winter one is kind of very large. Have you checked what's the impact on the winter mixed layer bias?
So winter mixed layer bias has not been improved or worsened compared with the baseline scheme. And so that could be due to some other processes affecting the deeper mixed layers. And so it could be due to some other parameterization or EPPL itself. So yeah.
Other questions?
Hey, Aakash, nice talk. I wanted to ask about H, which you didn't talk about. So you said it was determined via physics, and I'm familiar with KPP, and a velocity scale might go into that H calculation. How is H done? Are the results sensitive to that H? I would think that would be a target area for, does the V affect the H somehow indirectly, or is there really no change to H?
It comes from Bob Hallberg's talk.
Okay.
So it comes from the implicit energy calculation, and it is parameterized by thinking about conversion of TKE to potential energy. And in a single column model, H is not affected if you change V that much. It doesn't affect it that much because it is strongly determined by the implicit energy conversion or calculation. So sorry, what was your second question?
So it does affect H, but just not much.
In a single column model force simulation. But in a GCM, the story is, I think, messy.
Any more questions?
I think there were people before here, if I may.
Yeah, you have a velocity scale that's not a function of depth.
Yeah.
But similarity theory says that it is. It tells you what it should be as a function of depth. Why have you ignored it?
Yeah, that's a really good question. In the paper I'm writing, I have an alternate formulation which has H in it. But in the previous paper, there was an issue because if you add H as an input, for the neural network, it might go out of sample. And I have averaged over H, and I've shown that the error is not much.
General non-hydrostatic processes with a focus on deep convection.
Yeah, hello. Can you hear me?
Yes, we can hear you.
Can you see the slides moving?
Yes, we can see your screen.
Perfect. So shall I go on? Well, okay.
What do I need to say?
Go
ahead.
Okay, thanks. Thank you. So I'm Quentin Jamet. I am currently a researcher at CHOM in France, and the work I would present is mostly done during my last postdoc at INRIA with, in particular, Étienne Mémin and Gilles Tissot. And so I thank the US Clavar and Commodore workshop for letting me presenting this work, where we were actually interested in a way of parameterization, general non-hydrostatic processes, but with a specific focus on deep ocean convection. So the broad overview of why we matter for convection. So you probably know all that, but just remind a few points. So it's very localized processes. So I've tried to spot them here in the left panel. So in North Atlantic, so they're Labrador Sea and Greenland Sea, so they are known as like controlling deep water formation in particular, and for the AMOC, which has like a pretty large ocean scale circulation. So there is clearly a scale coupling between very localized processes and a very large scale, large scale dynamic. And so another slide. So the aim of this work is to think stochastic parameterization for for improving climate models in particular. And so how things can be or are usually done in climate models. So that's basically with the traditional vertical mixing schemes, which are down gradient, as it was just explained. Where basically the schematic on the left so represent what happens and what tried to mimics. this downgradient formulation where you are actually extracting heat at the surface and to consume static instability that form at the very near surface. You represent the process with a diffusive approach, and so that's purely local, and grid cells mixes toward the depths until the static instability is completely consumed. So that's known as it has limited capabilities for convective events, in particular when they are deep. And so other forms of parameterization that have been that have emerged. So particularly in the it comes from the atmospheric community first, and then it's applied. It has been applied recently in the ocean community. So it's eddy diffusivity mass flux. And so what tries to do this this eddy diffusivity mass flux? I think you just had the presentation of this before lunch, but basically it augments the vertical fluxes of any quantity with a mass flux here, and basically it aims to represent the actually the transport processes that is at play during convection, and so that's a non-local effect and associated with current structures. And the benefit of having this representation is the creation at the base of the mixed layer of warming of the base of the mixed layer. So it's associated with entrainment, penetrative convections, and that's if you have one thing to remember on this slide is focusing on this specific spot here in the schematic where you actually have a peak in stratification. So what we are trying to do is to see how we can use stochastic approach for representing this and how skillful they are. And for the stochastic approach we are actually using is the location uncertainty. That's the short name of the formalism. So I will introduce it in a bit. Describe quickly the larger dissimulation of free convection we are using and applying this. And going on in two different applications. First one is a 1D vertical application for the temperature equation, and the second one is the 3D application where we will focus on the momentum equation. So the stochastic framework we use is the Lagrangian location uncertainty, and so the basic idea is to represent the trajectory of a particle as a resolved component here with a resolved velocity field, and uncertainties, which is encoded into sigma dBt, where dBt is a Gaussian process. So the schematic on the right try to give a picture of what that tries to mimic. So you have the resolved component trajectory in black and all possible other trajectories in colors. And we are in a continuous media, so depending on where the particle will end, it also will have associated uncertainty on property. So if it's temperature, it can be a bit colder or a bit warmer. So the process we will transport is also stochastic. And so that's the two ingredients, the trajectory and the process, are stochastics. And with that, we use the framework is based on a stochastic calculus developed by Ito, and with these two ingredients, we can derive a stochastic transport equation, which is termed here with the dt, and it has this expression. So you have the time increment at the first term, and then a collection of different terms. So the first one is the result velocity. So this one is acting on the gradient of the process of Q. So only considering this one with time increment is the material derivative we are familiar with, and so all others come from the stochastic derivation. In particular, we have here the stochastic advection with sigma dBt representing the stochastic flow. A diffusion term which ensure that the stochastic transport conserve energy. In addition, we have also a modified advection which can be which is called stochastic Stokes drift, and it's composed of the divergence of A and divergence of the noise. This term goes away if you assume that your noise is incompressible, for instance. So here you construct your noise with sigma, and A here is actually the covariance matrix of the noise. So this framework, it has been mostly applied for incompressible primitive equation and simpler set of equations like UG or shallow water. And so what Gilles Tissot proposed is a generalization of this formulation, but for compressible Navier-Stokes equations. So all the details are in the in this book of the workshop stochastic transport in upper ocean dynamic, so Stewart workshop. And but the bit of a context here. So what the steps followed is to account. So when we form a budget equation for a process Q, we account for source term on the right, and the source terms are decomposed in a resolved one and a stochastic one. And with this, we can then generalize the stochastic Reynolds transport theorem, which is I wrote down here. So you can apply that to any process, to any quantity Q that you want and that you know as a conservative property. And so that we apply it for kinetic energy, potential energy, and also for temperature. So to end up with a transport equation for temperature, we apply the conservation, so the stochastic Reynolds transport theorem to the total energy, which is decomposed this way. So it's kinetic energy, gravitational energy, and internal energy. So where internal energy hosts the temperature, and at the end we end up with a pretty complicated equation, which I summarized it here. So the first term is the stochastic transport of temperature, and a collection of other terms which are basically an interpretation or physical interpretation are written down here. So the AT represent the work of stochastic heat flux on the stochastic flow. So that's covariations of two stochastic processes. AU represent the covariance of stochastic pressure term with themselves. And on the right-hand side, we have a resolved and stochastic compression and dilatation effects, and viscous to the stochastic and resolved viscous contribution, and also resolved and stochastic drift work, what we call drift work. And so we identify the drift work as something similar to what is known in compressible large eddy simulation as a Perrot-Pitnal work, which has been in particular identified in a paper of Alwi in 2013. So the generalization here, it serves as verifying earlier derivation, and we can recover. We have verified that applying a Lomash and Boussinesq approximation, we can recover incompressible Navier-Stokes equations and hydrostatic primitive equation. But the benefit of having this generalized form is that we can also sit at the intermediate levels of approximation, which is of use for our work. So that's for the mathematical framework, and so we then apply numerical simulation to evaluate the capabilities of this framework. And so the simulation in particular is a larger simulation of free convection. So you have a block of ocean, which is the temperature increase linearly from bottom to top, and at initial conditions, and we extract heat at the surface at a rate of 500 watt per square meter. We let the model run for 3 days, and we have no rotation for now. equation of state is a linear one and temperature driven. So a short description on the numerics. So it's 1 kilometer by 1 kilometer by 500 meters. It has a 10 meter isotropic resolution. It's doubly periodic. So we have a non-hydrostatic non-Boostinec solver. And for advection, we use implicit Wino5 scheme for all tracer and momentum. Except for the vertical advection of temperature, where we use an explicit second order scheme, and that's because we wanted to control the rate of dissipation on the vertical, which is then done through like a very quite crude actually enhanced vertical diffusivity, which consumes static instability when it occurs, and that's particularly at the near surface. So first application of this is through the temperature equation. So we'll take a step back where we will for a time forget about stochasticity and just see what we can do in terms of deterministic case, and that was kind of a validation step for benchmarking. So if you take the temperature equation in a deterministic case and average horizontally, so due to the setting we use, the equation actually reduces to two terms: vertical temperature fluxes, one which is resolved. So that's turbulent vertical fluxes of temperature, and there is a subgrid scale also. And so then we can simply step forward in time this model with a very simple time stepping, and then recover. So explain the evolution of the profile of temperature. And so that's what I show here. So on the left panel you have the vertical temperature fluxes, so the total one in green, and the orange one is the resolved component, and the subgrid scale component is in blue. And so we have the resolved component, subgrid scale component, which is acting only near the surface as expected. And so it also hosts the surface fluxes we are imposing at the surface. So with this, if we step this model forward, we can recover the temperature profile after 3 days, which is the red dots, and the black line on the background is the reference. So now if we do the same with
2 more minutes.
Yeah, okay. If you in terms of stochastic approach, so you have here only, so same, there is a lot of reduction in terms of equation because of the setting, and here I only show the component which are associated with the stochastic transport, and other terms are all the other terms that I showed earlier in the equation, which we are still working on for now. So you have a modified advection, stochastic transport, and diffusion, and you can look. We can then look at how these terms behave and compare them with the reference case. So now the black curve is still our reference, but it's the vertical derivative of vertical turbulent fluxes, and in particular, what we are pretty happy with is what happens at the base of the mixed layer, where we see that the stochastic formulation is able to reproduce quite remarkably the signature of penetrative convection. And this is a combination of 2 terms. And I have to mention that these 2 terms contribute equally. So, okay, for this first application, I will try to go for the third application, 3D application. Try to do the best with the time I have left. So that's for momentum equation. So the idea here was that the vertical momentum closure we use are only 1D vertical schemes, and so they don't account for horizontal interactions. but this is a picture of a different basin or global high resolution simulation, and so their horizontal resolution. The horizontal grid resolution is of the order of the size of vertical plume in deep convection events, which reach almost 1 kilometer or so. And so we need to basically, so those simulations, in a sense, they are entering in a gray zone where we need to reintroduce the vertical dynamics, but we want to think of ways of doing that without solving a non-hydrostatic model. So for that, we get inspired by the paper of Klingbeil and Burchard and Pierre Garot, where they proposed a direct non-hydrostatic pressure correction. And so the idea is to augment the HPE equation with a pressure correction term, which is computed. So here in our case, it's in stochastic case through action of the stochastic transport on the vertical velocities. And for this case, we implemented that in a Croco. So we switch off our non-aerostatic solver and implement that in Croco instead. And this is basically the spectra we get. So the reference spectra is in black, and the one we get is in red. And also on the right, so this is kinetic energy spectra. And on the right, we have like also a PDF of vertical velocities at mid depth. And so we're still, we still have a bit too much of a high.
Can we wrap it up, please?
Yep. Yeah. Okay. So that's the PDF, and still work to do, but we are quite happy. And so for conclusion, so I let you there with the conclusion and summary, and I'll be happy to take questions.
Okay, thank you very much. We've got time for maybe one or two very quick questions.
Hello, thank you for your talk. If I understood right, you're doing LES with a vertical resolution of 10 meters. So I was wondering if you maybe check the convergence of the simulation, and if you can trust your LES results, let's say.
Yeah, that was a choice to have a not so well resolved vertical dynamic, but well, I think except for the couple of first grid points where we say, I don't know, maybe 30-40 meters below, the fact that the subgrid scale estimates are relatively weak. I think we are okay with it. I agree, it's not a great choice. What we wanted is to have a isotropic resolution. Okay, so that was the balance.
Okay, I think that probably we should move into the end of session discussion.
Okay.
Thank you very much. The note taker is Dan Witt. Thank you very much. Right. Okay, so Florian and I are to both so please, let's start with any comments.
I can just start with the last point, actually, because we had discussion with Greg during the lunchtime, actually, about the possibility to share LES simulations. So it's something that is ongoing within the climate project, I think. And we need to probably agree on a way to standardize or more or less to document the data but I think this is something that is on his way. Yeah.
Can I ask a question about that, a specific question? So what does that mean? Does it mean the full 3D data, or does it mean the result, the kind of average result?
Because we didn't, for me, it's single column. It's for me, it's not the 3D data, but I don't know if this is what you do. You do share really the 3D data, or
both are possible, but I guess 3D data takes more, you just need more money to store it. I think the interesting thing about the LES is that they're actually relatively easy. That's why everyone does their own. So the real value comes in from more sophisticated LES that maybe are comparable to observations, or I think, Dan Witt has worked on LES like that too, which that would require a serious effort, funding, but also people who want to write a paper about the data. And I think that's how that would happen if it was, yeah.
And there has been an initiative in the atmospheric community, something called Gables, for example, where they standardize a few test cases, and some of them are really based on directly from observation. So they use that LES simulation in a realistic or semi-realistic context, and they initialize it with observations, for example. And it's more challenging than just the academic case we can do. And it was within WCRP working group on numerical experimentation, something like that, a few years ago.
Number one was inspired by, at GFDL, we had a kind of recipe of everything we needed to parameterize. And I think we kind of have about 90% of it used. We keep on forgetting to turn on something sometimes. But I am actually wondering, is there anything that the broader community thinks is a process that we haven't actually considered putting into a model, and does it matter? I actually don't know the answer to that. And, I think we might feel like we know everything, but I'm actually asking just a general question, is that true? Do we actually think we've named every process that we need to give a name to and said this is now being parameterized?
I think that Gurvan is talking about near inertial waves all the time, that we should try to parameterize it. There is a paper by Marcus Rorum, I think, about that a few years ago, but I don't really know if it is really done in the models, actually.
So near inertial waves are a little bit tricky because they have very large spatial scales in the horizontal, but they're fine in the vertical. Our models do a perfectly good job of ringing at the inertial period. And so as long as we capture those shears, the energy sources, we might actually have a lot of the energy there already in the model, and it might not be something we need to parameterize the full pathway, just the conversion of the shears to 3D mixing.
Yeah, as I recall, Marcus's paper was based on CESM or whatever it was called, CESM, with like a daily coupling time at the time. And the big difference comes when you have a coupled model where you couple every 30 minutes or so. You get that energy from the atmosphere in there to ring it. And so any parameterization would have to know what the coupling is, how the forcing is. And so I remember us saying, well, we're coupling every day, every hour at that time. And do we really, what is it we need to parameterize?
Do we? Oh.
So one, maybe a little bit of a tweak on number one is maybe we do know many of the processes we need to parameterize, but one that a few people have thought about, some work I've done with Hamilton and Baylor and others, is how do these, can we parameterize, say, the effects of vertical mixing in the presence of some mesoscales? Do we know what the modifications are? I think this goes to more complicated tests. A lot of our vertical mixing parameterization done is very simple tests, so more complex LES could help with that. as well.
Well, the big elephant in the room when you get away from the surface boundary layer is the tides. The tides are the dominant source of either boundary layer, bottom boundary layer mixing, coastal shelf mixing, or by radiation of internal tides. They probably are one of the big drivers of the insonification of the internal wave spectrum through much of the ocean, and then the energy cascades to different frequencies through nonlinearities. We know that the tides will change over time. They are observed to be changing as a result of coastal development, as a result of changing stratification. The pathways for the propagation of the energy from the creation of internal tides to where they hit topography and break. We saw some of that earlier this week with Ashley's talk. That's something that there are steps toward that in various places. The TRM 121 effort, I think that's a large part of what's going on. But it's something that is not explicitly represented in large-scale models, and probably could be one of the dominant changing or changeable sources of mixing in climate models. We know what it is. There's a lot of complexity that goes with it, and there will be a lot of work figuring out how to do it right. But in a lot of ways, I think that's one of the big things to focus on, and we haven't put as much effort perhaps into that as we should.
Yeah, I think I just had that. We had a conversation last night about how in a high resolution model that resolves tides and part of the internal wave spectrum, then there's an opportunity to parameterize the unresolved part of the spectrum. But we don't have there's no work on parameterizing the unresolved part of the spectrum based on the part of the internal wave spectrum that we do resolve, right? That's sort of a futuristic, maybe, idea for mixing parameterization by internal tides.
So I have a thought about the second point, about if adding complexity is worth the cost. So I would say if you add complexity to the model and it improving performance, and know you can validate it, then it's worth the cost. But sometimes there might be other direction. For example, if we talk about biogeochemistry, you have 33 tracers. What if you use equation discovery and it tells you you just need 16 of those? Does remain important, therefore, as an example.
Any thoughts on number 3?
Yeah, I think number 3 is a great question. As we've gone to higher resolution with some of our regional models, not only have we discovered certain parameterizations we don't need to be on, but new processes that become even more important to parameterize, such as like river mixing and estuaries. And so thinking about how our parameterizations fail to hold when they interact with each other, such as mixing in the sub-mesoscale, and also as we change resolution in different parts of our models or things like that, I think is going back to those physical assumptions and clarifying them.
For example, Bill, do you think that KPP can be used all the way to?
Well, that's what I was trying to say before. I think the whole idea of an eddy viscosity should be rethought. We've seen that up here almost every talk, and it's not a fundamental turbulent mixing parameter. It's got dimensions for one thing, which no good turbulence parameter have dimensions. It's an analogy to molecular where things really do only operate in the neighborhood. But eddies mix much bigger than the local. So the whole idea of a viscosity, an eddy viscosity as well as diffusivity, and most of the talk's been diffusivity, not viscosity, how the two link and whatever, that's a scary one. I just don't think in the long term, eddy viscosities and diffusivities are going to hold out. There's easier ways to do it.
Okay.
Yeah, if you have an idea, which you have in some of your ideas on the entrainment depth, we just heard about that, the mixed layer depth, entrainment depth, and you know the surface value, a straight line's your best idea. It beats an eddy diffusivity profile and all that stuff, in which you have to get gradients to work right, and they don't have time in a diurnal cycle to get themselves all straight. Eddy viscosities or eddy diffusivities are good for maybe the mean flow, but you know, even an hour time scale is too short. They just don't equilibrate fast enough in the diurnal cycle. So there's one, you just bring a straight line.
Well, I would argue that we're actually coming close to just in the surface mixed layer, we got a straight line. And the depth to which this straight line goes is determined by how much energy you've got. The thing that diffusivity is giving us is just kind of a convenient way to tell you how this relates to everything else. And it addresses the objection that for some things with really fast processes, the ocean boundary layer isn't perfectly well mixed. There's some gases and things where, or you have a surface skin layer that is slightly warm or slightly cool and other things. In a lot of ways, the reason why we're using a diffusivity parameterization in the boundary layer is because we're saying a metric that we simply do not care about is the vertical gradients of a pretty well mixed boundary layer. We get the overall fluxes right, the depths over which the temperature is changing about right, but the vertical gradient is wrong. Admittedly, completely wrong sign, and maybe we don't care.
Just be more precise about the problem.
Well,
So. Yes.
implicit solvers for the momentum flux, which keeps things stable, but that requires a viscosity. And if viscosity is not a good concept, then the numerics need to be changed and still keep stable. And you heard earlier some things about adding increments. Well, they might not keep things stable. So there's a lot in number 3.
So I'm going to push back a little bit on the implicitness of the viscosity. The viscosity, the dissipation of kinetic energy, is a source of energy. We have lots of examples with explicit sources and implicit sinks, and they are happy as can be. The critical thing is the sink has to be implicit because that's the thing that does the regulation. The source has to be finite and fixed. If you have kinetic energy input from the wind, something like a U star cube times a nice fuzzy number that we can fit with LES and understand, and there's a lot of theory that goes into that. But explicit sources and implicit sinks is a recipe for stability that we found worked for a lot of things. And so the viscosity, the energy source from the mean kinetic energy, maybe we can get away with that being explicit, but finite and fixed.
Maybe. Nice.
So just to come back to something Teresa said about the coastal scales, they had to, through trial and error, I think, turn some things off. And it's a surprise to me that we're, even at coastal scales, we've crossed some sort of threshold where all of a sudden something that we used to call vertical suddenly doesn't work. Because I don't think our resolution going from 100 to 25 to 2 kilometer has started resolving something new in the vertical. A three-dimensional process that we're suddenly resolving. So that tells us that there's something wrong with the parameterizations or understanding of how we're putting those processes in already. So that's I think something that's very useful to sort of consider for the global modeling, the fact that it's not helping in the regional scales. There is something else that's sort of hidden behind that is there is this, when it's mentioned back here, interactions between the vertical and the rest of the model, the other parameterizations. That is something that I think is going to, I think every model developer has experienced the problem of, the algorithmic problem of maybe whether we call, say, KPP first and then something else, or GM first and then something else and so on. And you have a very different solution, and you have to think about how you're going to interpret or diagnose your model, because it really changes the meaning of the variables at some point in the algorithm. And when we start becoming comprehensive with, well, I think it's around at least a half dozen for global models processes. I can't name them, but I mean, we're going to add more, I'm sure. But when you've got that many, how do you put them together in a way that you trust the solution? And I'm expecting you to answer it.
No, but it's physics dynamics coupling.
I mean, in my view, I mean, that was a problem with earlier version of, I think, MOM as well. The thing is that these things, the terms that you're talking about, are on the right-hand side of the tendency equation, right? They are essentially dissipation terms. And they are not necessarily, depending upon the algorithm that you use, they don't necessarily need to use the most recent available field, which is inconsistent to begin with, because there might be statistic or static instability in those. If you base all of them to the previous values which you have available, then whether you start KPP first or GM first or whatever, it doesn't matter. At the end of the day, regardless of the order, if they are based on the previous n time step or previous whatever adjusted time step, then it doesn't matter what order you use. But it depends upon the details of the time stepping that you use, I guess.
I think you've just essentially translated what I said, which is, if that's happening, then it means that there's an interaction between processes.
No.
No, there is, because you're saying that a process is being affected by the fact that the stratification was changed by another one.
No, that's exactly what I'm saying, the opposite.
But the physical system should be interacting, because you're finding that over...
Not during incomplete time steps of a model. During a complete time step, yes, you're absolutely right. My problem is that if you use an incomplete time step to assess the intermediate physics, then that is a problem.
Fair enough. So I appreciate your point there, but then that's just one particular choice of how to get around that problem. If you wanted to be something which is, the issue is how do you add things together, and there were different solutions. It's part of what Bob was talking about, I think.
And I think the key point is you need to recognize which processes are contributing and which ones are regulating the state on timescales of order a time step. If something is contributing, it can be explicit, and that's fine if it's relatively weak. If it's something that is regulating the state, say in the mixed layer, the fact that mixing is what, vigorous mixing of vigorous turbulence is what gives you a well-mixed profile, that's something that has to be treated implicitly in order to get it right. You would not mix and then apply the wind stress at the surface, because you would get a profile that doesn't look anything like observations. On the other hand, the regulatory process, if it's the last one, is the one that'll kind of clean it up and make it look oceanic. You listed a couple there. GM, it has regulatory aspects. A lot of times it's regulating the state on kind of slower timescales, which is great, except when it isn't. Where you run into interesting challenges is when you have multiple processes that are competing to regulate things. If you treat them as separate processes, that's when the order starts to matter. In the surface mixed layer, lateral eddy processes associated with sub-mesoscale instabilities are fairly rapid. They have timescales of order a day or so near frontal regions. Vertical mixing is pretty rapid. It has timescales of order a day or so. And so those are the processes which are rapid enough that they really have to be considered together, because together they regulate the system.
Do any of the other early career researchers want to wade into this?
Peter.
No, are we happy the way the bottom boundary layer is parameterized or things like that? No, nobody sees any issue. The bottom boundary layer, for example, we have just this log layer and without any stratification or log.
Just a very quick comment. What about laboratory experiments? Are they of any use to improve parameterizations?
I think there wasn't many talks about surface waves, but when you have surface wave turbulence interactions, I think laboratory experiments are one of the only ways to actually get at a truth. Whether LES can try to do it, but we still don't know if they do the best job. So.
I just want to put the related point out there that field experiments could be thought about in the same context, especially in this vertical mixing context. Not clear what to do. I don't know, I don't have anything to add other than
that. Since Greg opened the box to surface waves, if you go to high resolutions, surface waves can be an important driver of submesosphere turbulence. So then you have to model them more explicitly as we currently do, right? So, and then we run into the problem how to do that on the submeso scale.
Okay, slight change of subject. So connecting forward to talks we're going to hear shortly or tomorrow and the session on general coordinates. So some of the work we've done, I think you will know, in MOM6 is to try and improve the vertical coordinate representation so we can reduce the numerical mixing. And one of the reasons we did that is because we have a strong belief that the circulation is closed by mixing, and if it's numerical, you want to have control over it. I have a secret fear, it's not a secret fear, we all agree on this, that we still have a lot of numerical mixing, and we're on the verge of actually reducing that numerical mixing even further. And the fear is we won't have enough real mixing to close the circulation the way we need to close it. That would be a very interesting place to be, but I'm not going to be happy about it. So we are actually seriously asking, do we know everything we need to know that we need to parameterize? That's what coming back to question one. So that's just a heads up. Maybe we are not as good as we think we are, and our numerical mixing will not go away, or it's not as bad as we think it is. But that's one reason why this is still a very pressing issue. Remember that the mixing closes the circulation. It's one of the key things we need to get right.
Numerical mixing. How are you reducing numerical mixing?
We're going to build a perfect model. It's a secret. We'll come.
Did you tell him? I mean, say it.
We've realized that we made some mistakes in the vertical representations and the reconstruction methods. So that's all being revised, and we'll clean it up. We'll explain it when we've actually proven to ourselves it works. Yeah.
You want me to say something?
I can say that. Then the next thing you need to do is invert your model to find the mixing that you need to close the circulation.
Good idea, but so I think that in a sense, it may be that we have way too much mixing in our models, and that the residence time in the deep ocean is longer than we think, and that maybe we're compensating for that in the way we do the surface forcing or the lack of dense water formation or things like that. So I think if we do get to the stage where we can get mixing down below, get numerical mixing right down, I actually think that opens up the door to really understand the problem of overturning and understand where that mixing is occurring and how much you actually need to close the circulation. And I think that's quite an exciting thing, actually. So. because I'll add one more thing. It's not just the total amount of mixing; it's where where it happens. So where it occurs will have a different effect on the circulation. So there might be a very small amount of mixing happening in an important place, and maybe that's all we need.
Just to clarify, a relatively small amount of energy going into mixing in places that are very stratified and stay stratified in key places, like some deep cataracts, the Romanche fracture zone or the Samoa Passage. There's persistent strong mixing in the presence of strong stratification. The total amount of energy that you need to do the irreversible water mass modification is relatively modest. And we know from observations that a lot of the changes in water masses happens in key locations that we are maybe close to resolving as we get to higher resolution models, but where there will be qualitative changes. For instance, if you have the same transport across a 100-kilometer wide channel versus a 5-kilometer wide channel, the shears go up for the same transport, the velocities get larger, and so the energies associated with the mean flow are able to drive the mixing, but they're mixing against a stratification. Our estimates of the energy budget required to close things might be fairly different than when Walter Munk first looked at this in 1966 and came up with a long and imaginative list of all the processes we might include, but an estimate on the amount of energy that would be required if the mixing is very widely distributed instead of if it's closely localized in places of persistent strong stratification and shears.
So I'm very interested to hear about this perfect model. If you build it, and they will come, yeah. One of the sources of mixing that you might not capture and might help get more antarctic bottom water to upwell is the thermobaric circulation. So if this is thinking about having a layered model and those layers are neutral surfaces, then I mean, I'd have to think more carefully about this, but I think you might not be able to capture that feature of upwelling that happens across the neutral tangent plane when the flow is allowed to move horizontally and due to the thermobaric effect. But if the flow is constrained to be in neutral layers or ispignal layers, then that possibility is abandoned. And I think there's some estimates of the amount of upwelling that can give, which are order 5 sphere drips or so. So it could help.
Paul, do you have your hand up there?
Maybe the last comment. Last comment in this case. No, not you. Not you.
We have about 2 minutes left. Okay. So I just wanted to go back to the question that we had on day one about observations. How do you think all the observational work that's going on could be helpful? You know, we've had the CPTs, we've had numbers of them. Is it time for us to re-engage with the small scale measurement community who are out, especially some of these recent North Atlantic efforts that have been underway? Any thoughts on that?
Well, yeah, I think that I know S-Mode, which was a long field campaign, or 3 exactly. They plan to run LES modes initialized by that, so that they have comparable results to that. And it's also actually can use it as a coupled boundary layer experiment if you're lucky. And then I think that could be a good standard test set to take another turn on the mixed layer parameterization. And we should force or ask for more these kind of experiments in different regions of the ocean, right? There's the idea of supersites. And I think it would be great if input from the modeling community how to design these experiments before they do them. Yeah.
So the new SWOT observations don't look like any ocean model or any ocean observations I'd ever seen before. They are showing a lot of small scale processes in vivid detail, or at least ones that are expressed at the surface. And that, I think, could go a long way towards identifying key places for process-oriented observational studies of where these observable now features disappear, where they break, where their energy is doing something. They stop being expressed at the surface, perhaps. And so I think this opens up a whole new set of opportunities. We've seen it a little bit with, for instance, the beam going from south of New Zealand across to Tasmania. That's a beam of coherent tides. What happens to it? Well, I think there's still aspects of it that are, whether it becomes decoherent but propagates away as other tides, how much of it drives mixing. We know that some of those things are going on. But I think that SWOT in particular is going to show places to go and look for interesting processes that we didn't even think we needed to think about.
So that's our time is up, and I believe we have a break now until 3:40. Thank you very much, everybody.
Okay, let's get started. This session is on recent developments in ocean modeling, but it is mostly on diagnostics. Even though there are only 3 talks, it doesn't mean that these are the only developments that are going on in ocean modeling. So these are mostly on diagnostic side. So our first speaker is Graeme MacGilchrist from University of St. Andrews, and Online Tracer Coordinate Diagnostics in MOM6 is the title. So 15-minute talk, 5-minute Q&A, and I'll give you a warning 3 minutes before 15.
Perfect. Thank you, Gökhan. Thank you very much. Thank you to the organizers for letting me come on and talk about this stuff. I think not only is this probably not the only ocean model development stuff, it's also not particularly recent, at least in a broad sense, in the ocean modeling community to be able to do this. What I'm going to talk about is online remapping to a tracer of interest that you might want to have your diagnostics on a different grid to what you originally had. This is obviously a capability that exists in different models, particularly MIT GCM has the layers package. A few different models have this. We had capability for this in MOM5, particularly for TNS. I'm going to give an update on some recent effort to put this into MOM6, and in particular trying to leverage some of the MOM6's regrid remap architecture to be able to do that effectively. So this is work that has been sort of sporadically done with Andrew Shao, and there's a few different sort of interested parties in this, including Henri and Stephen. Before I dive into that, a lot of people have asked me where St. Andrews is, so I'm just going to give a clarifying point on that. It is just a little bit north of Edinburgh in Scotland. It is extremely beautiful, and I am very happy for visitors at any time. It is always this sunny without any other days. It is climatologically the driest place in Scotland, which is what they tell you when you go to visit, and then you realize it's still in Scotland. All right, great. Okay, so let's get started. So a motivation for thinking about water masses or tracer coordinates. This is something that's been done in oceanography back to antiquity. It's how oceanography really started, was tracing TNS in particular in the oceans and trying to understand their distribution. The point being that we can tag water masses based on certain properties. Those properties are evolved in response to boundary forcing and ocean dynamics. So understanding the water masses, understanding the tracer dynamics is helpful in understanding the underlying processes in the ocean. And so this is done in this case sort of in both a sort of entirely sort of descriptive way, taking inventories of water masses in the ocean, but also in a more kind of dynamical or kinematic way in relation to kind of understanding the circulation in the framework of water masses. So why worry or why think about using tracer coordinates for ocean model diagnostics? And I'm going to sort of give 2 examples for why I think this is relevant. One is both that, as I sort of described previously, thinking about circulation or processes in tracer coordinates can give you fundamental process level understanding of the ocean dynamics. So it's useful for just basic science processes to be able to understand, for example, driving processes of the overturning circulation, relationship to mixing, various aspects like that. It's also, and this is maybe relevant to this crowd, a very powerful tool for understanding ocean model processes and biases, and for a development purpose can be a very useful diagnostic tool. So I'll give one sort of process ocean dynamics aspect of this, and this was work done by Jan Erik Tesdal at GFDL. And this was work where we took a water mass framework to look at the overturning circulation in the Southern Ocean and its response to surface forcing. So there were freshwater perturbations added to the surface of the ocean. And Jan-Erik looked in a water mass framework, here we are, in the two models. And I'm not going to go into the details of this, but this is density space, looking at the overturning and looking at the surface force water mass transformation, the changes in the water mass volumes, and then inferring a mixing process. And we found these very distinct results between the two different models and related it to the ocean mixing processes that are happening within the Southern Ocean. From a model diagnostic, or rather a sort of model development point of view, a lot of work has been done by Ryan Holmes in particular and others in Australia to use water mass frameworks, in this case in particular thinking about heat budgets within within temperature coordinates, to actually diagnose to high accuracy geographical and total distributions of numerical mixing, as we've heard a lot about the relevance of that and comparing it to the explicit diffusion. Or explicit mixing in the model. And more recently as well, Henri Drake has just led this paper and written up this paper, which is in revision at James, where we try to lay out a framework for doing accurate water mass transformations, closing layer-wise mass budgets within MOM6. Importantly, we had to do all of these diagnostics using output at the time step. So we ran a small configuration of MOM6 and just output every single time step. And that's what he used to do his diagnostics, because if you don't do that and if you don't have accurately closed budgets, you end up with processing errors as you do your averaging errors, as you try to find your, as you try to remap to your coordinates offline. So why do we think there's some potential in MOM6 for doing this? Well, MOM6 inherently has this regrid remap architecture built into it. It's finding grids and remapping variables all the time. So we thought there was some potential to do accurate online remapping to coordinates based on any arbitrary tracer. So at the moment it does its regrid remapping for its prognostic grid. It also does regrid remapping for Z-star and rho. And this is just an example of closure of some heat and thickness budgets and salt budgets on the in that space. So this is, yeah, these are three different grids. This is just showing the residual of those budgets. But there's a strict requirement that that the grid is monotonically increasing with depth. And so the question is what to do about tracers with non-monotonic or decreasing profiles, for example, temperature, salinity, or indeed biogeochemical tracers like oxygen, or even more fun stuff like ideal age or something, remapping to these spaces online and doing diagnostics in that space. Okay, so the approach that I took, which was my second attempt, because the short answer to can MOM6's regrid remap architecture be leveraged to do this for non-monotonic tracers is no. That's because the requirement for monotonicity is quite strict for reasons to do with its use in the prognostic model evolution. The first attempt to do this, we did some sort of sorting of the water column, but I realized halfway through doing this that the gradients of the tracer that you're mapping to in a sorted column are not the same as the gradients that you're mapping from the column that you're mapping from, and therefore you're introducing fundamental errors from the start. So I took a different approach, which was to take, so I'm just imagining here that I've got some diagnostic that I'm interested in this case, some tendency of a tracer, for example, or a heat content or something, an extensive property, and then a column where I have discrete temperature bins, effectively, or this is the water column, and this is just the temperature within that water column, so you can see I've sort of inferred its non-monotonicity. What I do is then take this profile and find the interfaces. MOM6 actually doesn't require monotonicity in order to find the interfaces. You can find the interfaces, no problem. It just then has requirements when it then tries to do the regridding. But it can find all the interfaces, and then I just define a matrix that basically maps the original grid, the source grid, the native grid, to a target grid of temperature. And I just remap that across. And then I get some now temperature space representation of the variable that I'm interested in. Okay, so this is some testing that then I did in the single column test case of the model. This is just a Labrador Sea profile, which I chose because it has this nice non-monotonic feature in the temperature. So this is temperature with depth, evolving through the year in response to surface forcing. This is it remapped to temperature space, so it works, which was nice. You can see the bolus of warm water that exists in the subsurface in this, and you can see the sort of slow walking forward of the surface mix layer into warmer temperatures during the year. One of the nice things about MOM6, which the architecture does allow, is that it has a variety of approaches to do the effectively the interpolation between the resolved temperature points within the model in a whole variety of different ways, different higher order or lower order schemes. So we can actually look at the sensitivity of the remapping procedure to those interpolations. So basically how you're finding your temperature profile within the column. And actually turns out, so it gets the broad profile basically similar. These are all the different schemes. Gets the broad profile fairly consistent, but actually there's errors that are non-negligible that show up here. So you can get 10 to 20 to up to 60 meters of difference in the thickness of any of these temperature layers, simply derived from the fact that you're using a different scheme to find your interfaces between the grid points. And this, yeah, so this is the anomaly relative to the mean. And if I look at the standard deviation of that progressing through time, you can see that, yeah, in these layers that are thicker, you get these fairly substantial thickness differences depending on which scheme you use. And I don't think that, you know, a lot of people do conservative remapping to different temperature spaces, to different tracer spaces. There's not been a whole lot of approach to understand the actual, you know, most people will just assume a linear profile between two temperature points. There's an irreducible uncertainty associated with how you do that because you don't know what the temperature is between the points in the model. Okay, so just an example to potentially show some of the value of this procedure. There's another test case in MOM6, which is the downslope gravity flow and the configuration of that. Oh, and just before, so I'm going to look at actual trying to diagnose some of the water mass transformation budget within tracer layers. So this is from Henri's paper, and just a refresher on what a water mass transformation budget does is that for a water mass defined by a tracer, which has some contours within the ocean, so in this case, our tracer is lambda. It has contours and it has various boundaries at the ocean surface and some arbitrary defined boundaries. Okay, I see why people were having trouble with this. I did some practice on this and it seemed to be working out fine. No, I've lost it. Okay, it doesn't matter. This red area is our kind of area defined by the tracer and some boundaries both at the ocean floor, ocean surface, and arbitrary boundaries that we can define. The evolution of that mass or the mass within that, but defined by those tracer between those isolines of that tracer is a function or is set by the overturning circulation across our any sort of imposed ocean boundary, a surface mass flux, transformations that are happening both at the boundaries, so boundary forcing, and then transformations that are happening due to interior mixing. And then there's always going to be a residual piece in an ocean model. You evaluate the transformations basically based on the, oh, I'd love to see that again. There it is. Okay, the tendencies of the tracer itself integrated within the domain of interest. What you hope for if you get all these other terms right and closed properly is that your remainder, your epsilon here, your E here, should be your spurious mixing left over, the contribution to the water mass transformation associated with numerical mixing. Thanks. So this expression here relies on very accurate closed budgets and closed budgets that translate not just from the native grid, but into the new temperature space that you are working in. And that does not happen in MOM6, unfortunately. And so this is a problem that's been kind of a bit recalcitrant for a while, and it is actually related to the point that Gökhan was making before about the fact that the model is updating its grid persistently throughout the time step. So basically you end up with a situation where some extensive quantity, its difference between the next time step, the last time step, is not necessarily the sum of the tendencies of all the processes that have left it. And that leads to this error that can be non-negligible. So this is something that actually Keith Lindsay solved, wrote a pull request for it for a different way of doing the diagnostics, but it's not yet been pulled into the main branch of the code. So we can do this. This is not just a problem for tracer diagnostics, this is a problem for the Z-star remapping as well. So budget's not closed. So I'll press on anyway, just to look at one specific process rather than trying to kind of look at the full closed budget. So this is just the example of the downslope gravity flow. So this is what the test case looks like. You get this bolus of salinity that flows down the slope over some amount of time. What's quite nice actually is that salinity, that little bolus is also constrained basically by in its temperature profile. This is a 1 degree kind of, it's warm and salty basically, and the rest of the ocean is cold. And so what I decided to look at was the evolution, remap basically to everything warmer or colder than 0 degrees, which is basically following this the boundary of this water mass as it flows down the slope. And you can see, oh, geez, oh, I'm giving away the answers. Oh, no. Okay, so you can see the evolution of the thickness of that layer, the thickness of water warmer than 0 degrees as it progresses through time and in space there. Okay, so I can actually then evaluate the water mass transformation due to the vertical diffusion, which is the only thing that's really operating in this model, as well as an explicit, a numerical mixing, which I'm not resolving here because I've not closed the budget. But this is it for the Z level case. But the nice thing about this test case is that it was also run in a number of different, with a number of different prognostic vertical coordinates. So we can look at the sensitivity of effectively the mixing across that 0 or 0.5 degree isotherm associated with the vertical coordinate for this downslope flow. Oh yeah, okay, so that's that point. So there's also a sigma level coordinate, there's a rho 2, and then there's a layered coordinate which doesn't have any diapycnal mixing across the boundary. And you can see, you can map them all out. Now the discerning amongst you will realize, so this is basically movement from cold water to warm water. Yes, from cold to warm. It shouldn't go negative, so there's clearly some errors in what I'm doing, because then you're basically mixing up gradient, which is not what we want to do. But what we can see is that, at least in terms of the orders of magnitude, is that indeed, as we might have suspected, the sigma coordinate, the terrain following coordinate, has the least amount of mixing across that boundary, right? It's the most stable. And you can see that even indeed in the profile of temperature as it flows down the slope. Okay, so just a bit of ongoing work. First thing is really to implement Keith's budget closure approach to make sure that we are closing budgets on remap coordinates. To really significantly improve the efficiency of this weighted remapping that I've developed, it is not efficient. So we'll need to chat to people, developers, about how to do that. And then finally, to implement it for any tracer coordinate. Currently, it's just for temperature, but there's potential to do this for any tracer within the model, including biogeochemical ones. Okay, take-home messages I'll just leave up. Tracer coordinates good, can be used to expose biases and understand, but there is an irreducible uncertainty in terms of how you define that profile. Thanks. Thank you.
Any questions? Go ahead.
Yeah, thanks for that, Graeme. Previous slide, quickly, you said that you implement remapping into any tracer coordinate, but I thought you said earlier that you can't do that because it's not monotonic. What is it?
Oh, sorry. When I say remapping, I mean this like weighted remapping histogramming approach that I've input. So I can, yeah, we can do that for any non-monotonic tracer the way that I've implemented it. It's just that we can't use the regrid remap.
You can produce histograms, but you can't go after that, the next step. Okay, good.
What do you mean by the next step? What do you mean? We can't do it using the regrid remap architecture that's existing already. So I had to write basically a weighted histogramming approach.
So that's
separate to the kind of existing architecture.
Got it. Okay, thanks.
But that means that you can do it for any tracer. Right?
Yeah,
like
that's good.
Yeah. So anything that you can think up in your favorite tracer.
Any other questions? Wow, this is one of the best.
Just so, I guess. Yeah. There's no from Scotland. I'll punch them if they say anything mean.
Well, we are going to have the next Ocean Sciences in.
That's right, in Glasgow. Come by.
Cool, Graeme. That's really, really cool. This is going to be a really strange, dumb question, perhaps, but could my favorite tracer be PV?
Of course.
Cool. So you could like do a PV transformation with this and do a kind of cool budget approach with that.
You can. I mean, so some qualifications that other people, the developers, may be able to know, but PV is obviously not a tracer that's carried by the model. Whether you could do this on another diagnostic, so obviously you can calculate PV in the model. I haven't, because I've just done it for temperature, which is obviously a prognostic variable. I know where that is in the code and I know how it can do that. There would maybe be some wrangling to do it for a derived quantity as well, and how you carry that through the model, and whether you can get it past the efficiency police.
Bob looks really confused. Do you have any questions? No, okay. Okay, if not, we'll switch over.
Thanks, everyone. Yeah, of course.
So our next speaker is Spencer Jones from Texas A&M. And Spencer will be talking about online Lagrangian particle advection in MOM6.
Okay, hello. Yeah, I'm going to talk about online Lagrangian particle advection. Yeah, I mean, I'm not going to motivate that much. Basically, I want to know about my friend, the water fossil, my friend, the water fossil, and where is he going to go in the ocean? And yeah, this is work that's in collaboration with Kayla Uyeda, who was a gap year student with me and now is a PhD student with Henri Drake, Lou Yu Sun, who's at the University of Maryland, and then Alistair, Matt, and Stephen. And yeah, mostly this is a project funded by NSF. So yeah, we're going to think about how can we do Lagrangian particle advection online in MOM6 first. Why do we want to do that? Well, online particle advection has some advantages over offline advection. So online particle advection is typically involves running particles along with the model, whereas offline, you're going to have to save your particles, save your velocities, and you're going to take those velocities and use those to advect your particles. So that's what offline advection is, right? And so how frequently you save your velocities it really affects the accuracy of your particle trajectories. And so you can save more output and get more accurate particle trajectories. But when we go to this kind of high resolution, fast timescale model space that we're starting to be in, saving this much output to get accurate trajectory starts to be a really big problem. And so we would really like to be able to do online particle advection because it avoids this kind of huge output problem. And so, yeah, we're going to advect particles as part of the model run. But most people are going to be worried, right? MOM6 is not a traditional coordinate model. So we're going to need to do something different. First, I'm just going to show you a little bit about how people usually do it, because I think it's kind of hard to get to the place where I am until you understand how people usually do it. So usually in a model where the grid is stationary, you have a U, a V, and a W within each grid cell or at the edges of each grid cell. And the most common thing to do is you integrate U linearly in the X direction. So like this, right, you're going to have U that's coming into the side of your box. And this is an example that I've made up where there's land on two sides of the box, so there's no velocity. So you're interpolating between your incoming velocity and some zero velocity on this side. And then you also will have V interpolated linearly. In my example, we don't have V in the Y direction, and W is interpolated linearly in the Z direction. And so in my example, I have no velocity at the bottom, and I have some velocity at the top, right? And if you have a decent ocean model, the mass that's going in on this side, or the volume that's going in on this side, and the volume that's leaving at the top are going to balance. We would really like that to be the case. This scheme, you kind of will notice this is a kind of weird. Why are we doing this? Because if you interpolate U linearly in the X direction, V linearly in the Y direction, and W linearly in the Z direction, but everything is constant in the other two directions, right? That means you're going to have some places where the velocity changes at an interface abruptly. And so why are we doing that? And we're doing that in general. People do that because this is a mass conserving scheme. What do we mean by a mass conserving scheme? So that's my next point, is what do we mean by a mass conserving scheme? Well, in an ocean model, we generally just think it's mass conserving if the flow that's coming in equals the flow that's leaving. But if your particles need to experience mass conservation, right, they are actually experiencing velocities that vary within this box. And so we want to be able to get to a place where we can subdivide our box into an arbitrary other boxes And within any arbitrary box, you're going to have an equal amount of mass coming in as leaving, and that will prevent you getting clusters of particles at one edge of your box. And so this is what we do in a kind of typical situation, right? We have this scheme, so U is coming in, and so because U is totally uniform in the vertical within our grid box, if you subdivide your grid box, you end up with half the area for this subdivision, and so half of the amount of mass is coming in, and then you're halfway up this from the bottom to this interface, and so halfway up you have linear interpolated W, and W is your mass across this interface is W over 2 times your area. So we're all good. Everything is mass conserving. This is just an example of a scheme that's not mass conserving. So for example, you might decide, oh, well, I really would like my velocity to be small near the bottom because I have land. But if you do that, that's not actually mass conserving. You end up with less velocity coming into this subdivision of your box and the same amount of mass leaving. And so you're going to have fewer particles coming in than you would actually want. Okay, so we're already not in MOM6. So now, what about in MOM6? Well, we can't use a traditional scheme because W doesn't exist. So online, we don't have W, and I have no desire to calculate W online. And so we're going to have to do something else. And so during the dynamic step, the layers move together with the fluid, and hopefully we can use that. And the order of operations usually goes like this. We start with some initial state. And then first, we do some diabatic processes. So that would be evaporation, precipitation, and mixing tend to happen in this step. Evaporation and precipitation, I'm going to kind of gloss at the moment. It's a pretty hard problem what to do with particles when the water is evaporating. But during the mixing, right, no actual fluid parcels are moving. And so we're good. We don't need to think about that too much. And then usually they do a regrid remap step next. So that's just where you move the grid and remap your fluid properties onto the new grid. Again, the fluid isn't moving during this step. And so finally, there are these two bits of the actual Lagrangian step, which is where the fluid moves, that you have a time when the resolved velocities are used to advect the fluid, and then you have a time step where the subgrid scale velocities are used to advect the fluid. And so these are the times when we're going to move the particles. Sometimes the subgrid scale velocity happens first, sometimes the resolved velocity happens first. There are some different decisions, but yeah, basically we are going to focus on this step because this is the step where the fluid actually moves. And so the kind of main idea of what we do is on this slide. And that is we start with some initial condition, right? And what the particles are doing is they're maintaining their vertical position within the layer. So the green particle starts at the surface of the layer. And during the Lagrangian step, the dynamic step, the particle gets advected with U and V, but it's at the top of the layer, and it will be at the top of the layer after the dynamic step as well. The red particle over there, right, it's going to be kind of a little bit above the middle of the layer. It gets advected. It ends up somewhere else a little bit above the middle of the layer. And then you have the blue particle, which is somewhere in the middle of the layer. It ends up in the middle of the layer. And the white particle, which is at the top of the layer, and it gets moved in U and V. And the layer also moves, you'll notice, right, in the vertical, but it stays at the top of the layer. So the particles are going to stay in the place that they are within the layer. Now, you might say, how are we going to have mass conservation in this situation? And the answer is, we do a very similar thing to what they do in a fixed coordinate model, right? We just interpolate U linearly in the x direction, V linearly in the y direction, and then the particle maintains its fractional position within the cell, and it turns out that is mass conserving, right? Because in this case, this is MOM6, so the velocity into the side is equal to how much the interface moves in the vertical, and if I took an imaginary interface, which had particles spread along it, right, that's halfway up, that imaginary interface is now going to move at half the speed because it's the fractional position in the layer is maintained. So if this doesn't move and this moves, this is going to move at half the speed of this top interface. And so we have mass conservation, half of the water goes in and half of the amount of movement happens. And yeah, the next thing to think about is our code has these two different modes. There's a mode where you advect the particles using the resolved velocity only, and then there's a mode where you can advect the particles using the full residual velocity, so including both the resolved velocity and the eddy part of the velocity. And now, of course, like if you're in a high resolution situation, probably these should actually be really similar because the eddy part of the velocity is resolved. So when we use the resolved velocity only, we do this kind of sensible thing where we initialize, we advect with the resolved velocities, and then we freeze the particles in their location and allow the layers to move around the particles during the eddy step, right? And so they're experiencing both the U and V velocities and the change in thickness that's associated with those resolved velocities, but they are frozen in space when the subgrid scale step happens. And then when we advect with the full velocity field, we actually end up doing a pretty different process because the full velocity field in MOM6 is not encoded with a U or a velocity in meters per second. It's actually thickness weighted. It always carries around the thickness. And so we undo that, we divide by h, and we use this UH over h, which is the velocity that is relevant for advecting tracers to advect the particles. And so we have a single step where the particles are advected in this case. This is test case. Okay, I think we're going to do fine for time. Yeah. This is a test case which I did with a channel. It's 1 degree resolution, and kappa GM is 8,000 meters squared per second, so it's pretty high. But this is a feature of being in shallow water. You have to have a high eddy diffusivity, otherwise the model crashes. So yeah, we have the channel, we have zonal velocity, and then we have these isopygnals, which are quite flat. And what are we expecting the overturning circulation to look like? Well, we're expecting there to be, right, northward Ekman transport. This is like the Southern Ocean, so this is depth and latitude. Sorry, my pointer skills are not great, but we have northward Ekman transport, we have downwelling, we have southward Ekman transport in the bottom boundary layer, and then we have upwelling, and that's going to be what the resolved velocity looks like. And because we're in an adiabatic stacked shallow water configuration, we know the residual transport has to be 0 because there's no buoyancy forcing at the surface, and so we're expecting there to be a kind of exact match between the eddy-driven circulation and the resolved circulation. So what does the particle trajectories look like? Let's see. Okay, so the left one are online, the right one are offline, and I've just plotted them twice. The top layer, the top line is just to show you, right, which drifter number. So the pink and the gray, and each of them are initialized like in the same place between the online and the offline. And then the bottom row is the actual time, so you can sort of see that it's taking approximately the same length of time for the particles to make their way around the resolved circulation. Offline particle advection was performed using parcels. There were some small differences that I'm still trying to understand. And a little bit, one of the struggles is that I now have to debug both my own code that I wrote to advect particles in 1.6 and am I using parcels correctly to do this advection? So I don't know which of these has more bugs, but I do think that overall the online particles end up right. They start over here, they go down, and they go across, and they go up, and they end up really evenly spread. And I think that's quite a good sign that they end up really evenly spread. Whereas if you look at the offline particles, they do actually kind of end up a little bit more unevenly spread as they upwell. And so I think that seems to be an indication that mass is sort of being conserved a little bit more in the online case. Then I did the residual. The residual in this situation is very boring because we're expecting there to be no circulation in the meridional direction. But in the zonal direction, right, we can look, and this is actually a great place to look at the zonal flow because you really aren't, it's not complicated by any flow in the meridional direction. So the particles just stay where they are in depth and latitude, and they only move in longitude. And so this is a comparison of online versus offline, right? The red is offline and the blue is online, and they match pretty well. And I kind of understand why they don't match 100%. It's to do with some details of the initial location of the particles, which are very, very slightly different from each other. And so, yeah, so I'm really pretty happy with what this looks like. And then I'm going to do one more example. So this is a stacked shallow water channel, but now it's at 0.1 degree resolution. It's not, you will notice it's not at equilibrium yet. So basically the eddies are working and active right here, but basically close to the north and to the far south of the channel, we're not really in equilibrium. But yeah, so we have these eddies and we seed particles, and you can look at the online trajectories and you can check, do the particles stay in the layer that they're supposed to stay in? This is the most basic check, right? But the answer is yes, the particles stay at the same fractional position in the layer. And so that means that we don't have any movement of particles across layers, which is good because we're in an adiabatic configuration. And then, yeah, finally, the offline trajectories in this setup, because it's an eddying situation, right? They're very sensitive to what output frequency you do for your velocities. So I've done some very extreme cases where, in this case, I outputted velocities every 120 days. So I'm averaging the velocity over 120 days. And so the particles don't actually move that much because I'm averaging over the eddies. Whereas when I do offline trajectories over 1 day, they kind of look a little bit more similar and they do move around more, but still it does seem like, based on my current observations of these trajectories, it seems like they are moving more in the vertical, and they're moving, so that indicates that they're moving kind of also a little bit more across the isopycnals. I definitely do need to do a longer run. It just becomes a much bigger data problem if I run much longer than this. And so I'm like on the cusp of dealing with that. So that's kind of ongoing work. But my conclusions are, right, a traditional method won't work when we're advecting particles online in MOM6. The new method that I've come up with, together with Stephen, to be clear, conserves mass, and we can advect particles using both the resolved and the residual velocity field, though not at the same time at the moment. Online methods generally match offline methods at coarse resolution, and the online method should end up having less spurious numerical mixing and spurious vertical movement for high resolution. Thanks very much.
Thanks for the talk, Spencer. I can see how this works with like the stack shallow water equations in layer mode, but like with the full Ale scheme going on, let's take an extreme example where between time steps you switch between pure isopycnal or layered isopycnal or continuous isopycnal and Z star, right? Then the fractional layer doesn't actually, it's not correct, right? Because you will actually change layers.
Okay, but all of that happens in the regrid remap step. I hope you agree, right? And so what I have been bad at telling you is during this step, the particles stay at their location in space and they do not move along with the grid. And so that means that because whenever you do regrid remap, the fluid doesn't move, you just make the particles not move too, and then you So what you're doing is before the regrid remap, you're moving them to depth space, and then after the regrid remap, you move them back to the new coordinates. And that means that you always get a kind of consistent move.
Okay, so so the K, like if you're looking at the K index of the layer for the particle, it actually changes?
Yes, yeah,
Okay.
through the stack, right? Like
Interesting.
Okay, this might be pretty naive, but I was just wondering about the mass conservation aspect. So you've done a lot of effort to make it mass conserving, but there's sort of unavoidable numerical error both horizontally and vertically. Maybe vertically it's in the remapping step in this model, and horizontally, right? You're just your standard particle, however you're doing your particle movement. How important, how important is the mass conservation relative to those like numerical errors that are kind of unavoidable?
Yeah, I think that's a really good question. I think one of the things that's so yes, there are numerical errors, but when you run an ocean model, there are also numerical errors. And so my understanding of this is that the numerical errors that the particles experience are not actually very different from the numerical errors that are experienced by your salinity, for example. And so, yeah, this mass conservation turn, I think, ends up being really important. And particularly if you want to do really long runs and look at how particles move through a long part of the circulation, having mass conservation prevents you from having this problem of like the particles will end up stuck in one corner of one cell, which is really, really bad.
So we have two more questions, but very short questions and very short answers. Go ahead.
So, very interesting. So you basically also address this in parameterized simulation with the eddy transport. So I'm just tangling in my mind, for example, a parameterized simulation, you should also parameterize eddy stirring, which if you use particle to represent that, it's basically a dispersion process. So how does this process fit into your method?
I think the answer is I would love to do that in the future. At the moment, that's kind of more of an unsolved problem in general. Like, how should we be doing that? And so I'm trying to focus on the advective part first because we understand kind of what should happen. And then I think, yes, but I think that's a great idea.
Last question from Paul.
Yeah, I have three of them. You can pick whichever one you want. No, I'm super stoked on this because we use parcels a lot, and so it's nice to see this. First question is, when will this be like production sort of ready for others? Second question, how does it? Nah, you can pick your favorite. Second one is how does it scale if you go up like you do 1 million particles? How much slower does it make the model? And I think my third one is, can you with parcels, there's things you can't do, like tell how much volume's following along with the parcel, or you got to use some weirdo diffusion in the mixed layer. Because we're online, can we get around those? Can we get around that stuff, or?
Just answer one of them.
I guess my answer is, I am hoping to finish a manuscript about this and have it be available within the next 6 months. I have half a manuscript, so it's possible that could happen. All other questions I'll respond to offline.
Okay, let's move on. So our last speaker is Wang, and his affiliation is UCAR, NOAA GFDL, and University of Michigan. So take your pick. So he'll be talking about connecting the Great Lakes in MOM6, subgrid scale topography, and hydraulic control. As you noticed, all of the talks in this session are MOM6.
All right, everybody hear me okay? So last talk on the third day, I suppose it's the perfect time to get fresh up a little bit.
Wednesday. It's only Wednesday.
Oh, okay. Well, I need to get fresh up. So I'm going to talk about Great Lakes in MOM6. So this is this talk is on some of our initial effort to kind of simulate the Great Lakes in MOM6. So it's very much a work in progress. So what I'm going to, instead of showing a lot of results. What I'm going to do here is to kind of give you a background and sketching some ideas. So any kind of suggestions, comments, critics is welcome. So yes. So the first part, I'll just give you a brief background on kind of why we are doing this and what are the challenges, and then I will talk about a couple of numerical method or tricks to kind of tackle these challenges. That's subgrid scale topography and a prototypical representation of hydraulic control in MOM6. So the Great Lakes of North America, here's the picture, and or formerly the Laurentian Great Lakes. So it's a collection of 5 interconnected lakes between Canada and the States, and it has a total area of 244,000 kilometers squared. It can be as deep as 400 meters in Lake Superior. These supply 21% of the world's surface freshwater, which in turn supports 3,500 species of the plants and animals, and as well as 34 million people. It's important economic resources. It provides jobs for transportation, manufacture, recreation, and you name it. So the question here is, why do we care? Well, first of all, the Great Lakes is not that different from the ocean. It has a relatively large horizontal scale, so that's the Coriolis effect actually matters, and it's deep enough that it has a pretty decent thermal inertia. And similar to the ocean, its circulation is sensitive to the bathymetry, and it has mixing, convection, surface waves, and lake ice. But perhaps more importantly for the Great Lakes is that it's a regional climate driver. So the lake circulations redistribute surface temperature, and its dynamic and thermodynamic aspect is really important for the regional climates. And the representation in climate and Earth system models, the representation of the Great Lakes, especially a 3-dimensional coupled component, is rare. And a lot of people has attributed to the biases in the North America, as we see in the climate models, to the missing or insufficient presence of the Great Lakes. So our kind of goal here is to build a Great Lakes model with MOM6. And so there are 2 steps. So first of all, we're targeting on a regional model. So this figure shows the kind of the resolution, shows the topography and for our starting resolution at 1 kilometer. And so as a regional model, we probably need to move to the final resolution as we go on. And but the second step is probably a more interesting one here, is to have the Great Lakes as an interactive component in our global ocean model, and later on in the Earth climate and Earth system models, and which will have to run in a much coarser resolution. So we are really focusing on the world interconnection here because it's probably because of the previous work that's mostly focusing on regional models, has been focusing on the kind of separate lakes with closed domains. The closed domains is really kind of like a strict meaning here, is that not only they have closed lateral domain, they also don't allow mass fluxes at the surface, which is not ideal. And but there's good reasons for them to do that, and that brings us to the challenges of the Great Lakes, which is explained by this vertical profile of the Great Lakes here. So the first thing you will notice is that the mean water levels in the Great Lakes is not uniform. They're all above sea level, but they're not the same. And they are connected by individual, the individual lakes are connected by rivers, narrow rivers, for what it matters, and as well as the connection between the Great Lakes and the Atlantic Ocean. What is more, along these waterways, there are rapids, waterfalls, and rapid changes of the water levels. And probably the most important, or the most famous one, is the Niagara Falls. And in addition to that, we have also a bunch of man-made structures, locks, canals, weirs, dams, you name it, and international laws to control the flow. We don't have that in the ocean models. So what we are going to do here is to try to tackle some of the questions here with a few numerical techniques. So the first one is subgrid scale topography. So just for the kind of general audience, generally speaking, the model's grid is always 2 chords for the real world topography. And so most of the time, we just have one number for depth for each grid cell. The problem of that is, I think, twofold. First of all, it means that the depth at the edges of the cells is implicitly sometimes derived from the cell center depths. So this, for example, like there's no restriction on the connectivity from the topography, like showing on the left panel here. And narrow channels can never be realistically represented unless you do something with it. Secondly, the cell center depth is just one number. So you're losing this kind of vertical structure with a realistic water mass property distribution. And so the idea for porous topography, first, I think, documented in Apcroft 2013 is to use the simple profiles to represent this geometric effect, both at the edges of the cells and at the centers, to kind of account for this missing effect that we don't have in the model. And so we basically, for the implementations, to assign wave functions of depth for both the connectivity and the capacity of the cells. So how do we do the wave function? So there could be a number of ways of doing this, but the basic conditions we need to satisfy is that below the shallowest part, there's no connection. Above that is fully open. In between, we have something like smaller than 1 to constrain the flow. So and also the integral of this number should be equal to the mean. So Alistair proposed a 3-parameter fit in this original paper. Basically, we can kind of sort the topography and then using a monomial to fit which has the openness opening up monotonically over depth. And the special case of this is actually something we have been using for a long time in the model, is just to assign the real width to the channels, mostly to the well-known narrow channels in the models. So to add this into the model, pretty straightforward. We just added this coefficient based on wave function into the continuity equation. And I'm just going to be quickly skipping this. So there are some applications with the restriction on the cell edges. So the first one is in the original paper. Basically, there's a comparison between the high resolution and low resolution with the tsunami. And the arrival time is really comparable. And as extension, we implement the porous barrier in MOM6 for the global barotropic tides. And what we found is that, so this is kind of like very controlled case that we use the highest resolution topography as a source. And we found that is that with the porous barriers, with the subgrid scale topography at the edges, the tidal errors is significantly decreased at low resolutions, kind of replicate what we are seeing in the high resolution. So this is kind of like a global implementation for that. The second aspect is the so-called porous media. So quite similar idea, but applied to the cell center depth distribution. We basically can use this wave function to find the actual, the more realistic interface height in the model. Just to note that this does not help much with the one-layer barotropic case if the cells fully submerged, because remember that we need to have the wave function to be averaged to be the mean depth, so it doesn't really change the answer there. But it will have an effect with the wetting and the drying and multi-layer cases. Okay, so what does it do with the Great Lakes? So as mentioned, rivers are really narrow. This is 1 kilometer resolution. We are hardly resolving anything here in the rivers. So this will help with that. And also I use this slide as a motivation for the next part. So this is where the Niagara Falls is. And that brings me to the second part of the talk. So the hydraulic control. So we don't have, so during the hydraulic jump, there's a quick transition from supercritical to subcritical with great energy loss, extremely turbulent, hard to simulate. But there is a kind of long-standing theory with hydraulic control that we can basically infer the discharge transport from the surface height upstream. There's a very simple relationship with that. So what we're going to do, probably very naively, is just to put that into the model. So so basically, this is the momentum equation, very simplified, and but we can find a kind of critical velocity from that hydraulic control transport and use that as an upper bound of our barotropic velocity here. And so from that, the third equation, we can infer the additional forcing term and introduce that to the momentum. So whenever the velocity is above that range, above that value, we introduce this term to kind of drag it back. So this is some very preliminary tests that we did with a very simple case. So we have this 2D, we have this channel flow and just one layer, have a fixed inflow from the left, and then radiated out on the right. So what we're going to do is to compare the case with or without that term. So here's the results, and on the left, you have the case that we don't have anything, we don't do anything with it, so the velocity goes crazy at the jump, and but on the right, we have the velocity kind of clipped at that value, but also there's a compensation from the thickness and interface height, as you can notice at the end of the round. But so yeah, so it seems to be working, and I think we'll probably go from there to kind of implement that into for the regional lakes round. So that's my last slide. So to summarize, we plan to use MOM6 to simulate the Great Lakes, and the overarching goal is to have a dynamical interactive component as the part of the global ocean model and Earth system model. And connecting the Great Lakes is challenging, mostly because of the narrow rivers and the jumps. Subgrid scale topography may help represent these narrow passages between the lakes, and especially when we move on to the climate scale resolution. And we tried a prototype of hydraulic control representation in MOM6, and which seems to help with simulating the rapids and waterfalls. Right.
Any questions? I had one.
Yeah.
So in your related to first bullet, are you planning to, just to clarify, this is in a sense MOM6 embedded in MOM6?
Yeah, well, I mean,
or is it independent executables? Or well, they're both independent. I guess it doesn't matter. But
yeah, I mean the organic way of doing this is to have it as part of the global ocean model. So you can go from the Atlantic Ocean all the way up to the Great Lakes. But I mean that's the dream, I guess.
Thanks. This is really interesting work. I just wanted to ask you to speculate on, as we move to higher and higher resolution in the global ocean models, right? We're going to resolve channels more and more, you know, and these ideas of hydraulic control that we normally don't think about may come into play, or the fact that we might want to model these channels better. Is there a scale argument that might need to be made, or do you think that this will just kind of work if you tune it correctly, or like construct it correctly?
I guess that's a good question. I guess we're depending on when we are reaching to the regime of. I mean, this is our model is hydrostatic. So is there a limit of that to kind of actually include these processes? I don't know the answer.
Alistair and then Andy.
Thanks. So I think I think if I get it right, you've put the parameterization for the hydraulic control for the barotropic mode.
Right.
So two questions then. Have you checked that if you were to just apply that everywhere, that it doesn't do anything except where you need it for the waterfalls? And then second one was, if you were to think about to do this for layer by layer, as Andrew suggested, when we get to high resolutions, we're going to want to have that kind of parameterization for interior overflows. And it would be interesting to know if that's viable and to take advantage of the subgrid scale topography.
I totally agree. And for right now is that so what we what we have implemented is a switch. So basically, kind of like failsafe. It works kind of like a failsafe. As long as if the velocity goes supercritical and we clip it, and so the question will be that if we have some places that velocity will go supercritical that we didn't really notice. So
if this goes into the ESM, presumably you needed an ice model, but the ice is different to sea ice. Do you have a lake ice model?
yes, we'll start with this too and make modifications accordingly.
So Paul and then Bob has the last one.
So it's only 4 questions this time. No, I'm kidding. Yeah. I grew up on the Great Lakes, and yeah, I've never thought about like the importance of the circulation of the Great Lakes being important to climate. It's more the buoyancy fluxes, you know. Like,
it's really large.
It's just
there
like
are circulations.
Yeah, I guess. Is there evidence that the circulation of the lakes really matters?
I mean,
for me, it's like
surface temperature distribution. That's what we know.
Yeah.
I mean, like taking Lake Michigan, for example, the north-south gradient won't be the same without the circulation.
Cool. Thanks.
Thank you. Okay, last question, Bob.
So on this question about the applicability of the hydraulic control condition everywhere, it's upwinded.
Yeah.
And if you look at the formula, the biggest thing is square root of G times the depth of the ocean, which means it could apply anywhere in the ocean where the speed gets larger than that. In the deep ocean, that's 200 meters a second. In shallower waters, it's smaller. And as you get to wetting and drying, this is actually going to help with the drying phase where you effectively have a hydraulic control as things are drying out. But if you had extreme cases like the Chicxulub crater impact in Mexico and you're simulating that, that's a big enough thing that it actually has a hydraulic jump in the middle of the ocean. And so you could do that simulation and it might work. Or in a more realistic, more pedestrian case, we are suspecting that this would allow you to have tidal bores in certain large rivers. And so it should be very general. And the theory is really old. And no one's written anything about it forever because it works really well.
Is that a question or a comment?
That was the comment, kind of clarifying a little bit of this question of why are we doing this and how general is it?
I mean, related to that, just like we do actually have a simulation with MOM6 for the dinosaur distinction event. Without this, so it might be an interesting question to kind of take another look at that.
Well, let's thank our speaker one more time. So we have a very short time, 18 minutes for discussion, and I just want to, where's Anna? Anna is the note taker. So thank you, Anna. So as now you got used to it, we have again questions. Some might be easy. I can't even remember the questions. Okay. So only 3. So what are the big challenges for ocean modeling, or what challenges are holding back progress in ocean modeling? What new diagnostic methods should be considered? And we have seen quite a few of them this afternoon. And what efforts are needed to make the use of our models and analysis of simulations easier for the community? And we have seen, or we have that discussion actually the first day as well. Steve,
So on number 2, somebody said the magic word that I've been chasing for years, and that is potential vorticity with water mass analysis. I think water mass analysis removes the diabetics, or removes the adiabatic stuff, and it's only interested in the stuff that's crossing the coordinate surfaces, whereas so you basically remove waves, you remove a lot of the dynamics that a lot of us focus on for other reasons. And I'd love to see, and one of my favorite papers from the atmosphere community was Brian Hoskins' 1990 something called A Potential Vorticity Theta being the potential temperature view of the atmospheric circulation. I would love to see that, maybe replace theta with neutral density view of the ocean circulation. And I think that we need to get better diagnostics of potential vorticity, and there's some work that the French have done, Yves Morel, brilliant piece of work, and Jonathan Gula, looking at how you should diagnose PV in the models. And we were doing a lot of water mass analysis diagnostics. So I think bringing those two together would be a fantastic new way to look at diagnostic methods for the ocean. Henri.
Are his tools addressing that or not? I thought that there was some kind of PV element in those, but I can't remember.
No, we haven't applied it to PV. And you have to deal with this stuff with monotonicity that Graeme was talking about too.
Okay. This?
I think this is a question for the broader community. I'm about to dive off into PV budgets, not with water mass transformation yet, but just can I get like a PV budget and a couple of models to close? And I'm kind of curious, what ocean models out there have diagnostic tools for PV budgets to start with? Nothing fancy like, binning it by density, just like in whatever the native coordinates are.
Coco?
Yes, so Steve mentioned the name of Jonathan Gula, and I think he has been able to close the PV budget in the Croco model. So you should ask him if you want. But it's really, yes, everything has been hard work, and it's very intrusive in the code. But anyway.
Go ahead, yeah.
I closed the PV budget in the MIT GCM with a linear free surface and fixed Z levels. So I could potentially help if you want to get in touch.
MIT GCM. Any other comments or questions, or? People are getting tired after third day, I guess. That left.
Yeah, thank you very much. I cannot stop myself in asking, you basically have this top question, what are the big challenges in ocean modeling or for ocean modeling? Realizing that ocean models are usually also a component in a coupled model or an Earth system model. Would you actually come up with a different answer if you consider that at the end it should be really a component of an Earth system model?
Well, I mean, that question was phrased simply because this is an ocean meeting, but I mean, you are right. Some of the questions can be, the challenges are similar in a coupled environment as well. Like take the Gulf Stream, I mean, I'm just giving an example, separation issue from the North Atlantic current. You see that in ocean-only simulations as well. As soon as you get to the coupled system, it gets it gets stronger. Similarly, upwelling biases are still there in ocean only, and then they get exaggerated, or I'm using the wrong word, probably not exaggerated, but amplified in coupled systems. So yes, you can probably say the same.
Well, there are these aspects, but at the end, if you want to do long runs and simulate climate change and sea level change, of course, we know that the seafloor is moving up and down. And so all these things related to sea level, for instance, including the freshwater into the ocean and many things, is that already there, or is this being thought of, or?
Well, I was going to say something different, but I could respond to that. There's a lot of the growth in the integrity or the capability of models to do sea level is growing. We're doing better tides, self-attraction and loading. We can presumably do the static equilibrium problem online now, where you melt Greenland and you see how the GOA changes, the GRD effect. And that's a capability that I've been looking for 15 years. I think that would be wonderful to do. I think some people are putting in the GIA, or at least getting to the point where you can put that into the models as well. But some of that is like, do you need it versus, you know, you could do some of that offline. But I think the GRD online is an interesting dynamical question. Is there feedback to ocean circulation? That hasn't been answered until you really do that problem. So I would say that the capability for sea level and the wetting and drying stuff, coastal inundation, we can do that in MOM6. At least the capability is getting there. So.
Well, this is good, but I think the online, offline, if it comes to terrestrial ice sheet melting or glacier ice melting and so forth, you really want to have the lifting up of the seafloor, because that actually is the buttressing that influences also the flow of the glaciers. At the end, for the long run, you really want to have that in online, not offline.
I'm a different topic, so let these guys keep going.
Okay, Bob, are you addressing this one? Okay.
Yes, it is becoming available online. Stephen Bruce et al. At Los Alamos have worked out how to do the self-attraction and loading online. There remain challenges with how you handle the thermodynamics properly when it dries, handing things off to the land, or as things thin, making sure that a heat flux into the ocean has a place to go in the mud at the bottom of the ocean. But I think these are all things that are going to be relatively tractable. The self-attraction, online self-attraction and loading, making it work efficiently is something that the big breakthrough 2 years ago. And it's something that's being propagated to realistic global scale models and works pretty darn well. Well, that'll cause sea level rise, so we'll have to allow for wetting.
So Paul and then Steve.
Thanks. I just wanted to bring up salinity restoring. It'd be so great to get rid of that. And also, yeah, air-sea coupling, you know, kind of sick of this fixed atmosphere, especially in polar climates where we're trying to look at sea ice. It's really disappointing.
So back to number one and getting to the Earth system question, sort of what Detloff was hitting at. Big challenges. I think there's an interesting challenge, and atmospheric people are really, really interested in this problem called the pattern effect. The NCAR's done some important work showing that there could be a role for high resolution ocean in the pattern effect. There's a lot of potential relevance for the Southern Ocean melt and freshening for the pattern effect. So it kind of really, if you start to get tropical atmospheric people interested in the Southern Ocean, that's a pretty important milestone in my mind that you know, gives some, you know, hey, that's cool. You know, people do care about the Southern Ocean more than those that are just doing that problem. So I think that could be, you know, is that only solvable with high resolution models where you have these wiggles and eddies and stuff like that is a big question. And the coupling is there, the high frequency coupling with a high resolution atmosphere. I think you all had a 25-kilometer atmosphere with a 10th degree ocean and you got a good pattern effect. So that what people mean when they say the pattern effect is the different response to a surface warming depending on where that response is on the planet, at high latitude or the tropics. And there's a cooling in the southeast Pacific and cooling around the Southern Ocean, Antarctic circumpolar current in the south of that the couple models typically don't get. And a lot of atmospheric people are saying, well, it's this and that in the atmosphere, and some are saying that there's an ocean component too. I think that's exciting because it does allow for us to say, hey, there's some relevance potentially of really ocean processes that have big effects.
Teresa?
Yeah, I was just going to say briefly, work on getting rid of sea surface salinity restoring is something that is going on at GFDL. It does involve changes to the coupler. Matt Harrison has been working on this. So we're aware, we're fixing it, but I think it goes back to thinking about the ocean model, not just on its own, but in relation to these other components of the Earth system and how to sort of further blur the lines between the different models.
Andrew, behind you, Gustavo.
So one of the things that's been really interesting, kind of like seeing how other domains are starting to analyze their stuff, is that we're at the point now where oftentimes it's actually faster to rerun a simulation than it is to load the data from the simulation. And I think with the interesting advent of things like Oceananigans, right, there is a potentiality that we can do a lot of the diagnostics just by rerunning it, like implement diagnostics. And in some ways, we already do this, right? Like MOM6 has this whole regrid remap scheme, which is a form of computation that we used to do offline, right, when we wanted to kind of compare grids. So I just want to put that out there, that this is a really interesting time where compute is both cheaper from an energy and carbon point of view than trying to store data, and is also faster in human time. So just food for thought from other things that we've been seeing in other domains.
I was going to add to what just Steve said, essentially, and that comes back to probably what Detlef is getting at as well. I mean, so far we have seen examples at this workshop as well. There are still quite a lot of persistent biases that the community as a whole has not addressed. And Southern Ocean Challenges is one of them, and it's really emerging, especially with, as Steve indicated, with high resolution ocean models and maybe coupled to quarter-degree atmosphere, that's helping. So that is one. Gulf Stream separation, North Atlantic current, and we still have problems because it depends upon so many things, right? The bottom topography, vorticity budgets, inflow, outflow, whatever the water mass is, whether you are doing it properly in the Nordic seas, that matters. Regional models tend to get it right, but as soon as you go to a global thing, high resolution helps, but it's not the solution. Warm biases of the, whatever the western sides of the continents, usually there in most of the models. Double ITCZ in coupled systems, it shows its ugly head occasionally and it disappears, but it's what controls it is still an issue. We don't really know. At least I don't know, maybe people know. And I mean, there are numerous biases, but I don't see any concerted effort in a sense as a community to address these. And that's, I think that would be my answer to number one. And people are doing bits and pieces of it. And there's quite a bit of model sensitivity to these things. And I feel like we are not really tackling the, well, I mean, they are there, persistent biases. That's why they're called persistent biases. They've been there for 40 years. People tried many things, but are there new ideas to tackle more? So Bob wants to answer that question.
So I think one of the things holding us back is we make a number of approximations. We all make the same approximations in the ocean. So a lot of our models are Boussin-esque. We know that that changes things subtly. We've assumed that the tides didn't matter in climate. We just kind of ruled them out. Self-attraction and loading might matter in the Southern Ocean. There are a whole series of things. And we've forgotten a lot of the approximations we made just because we're so used to them. And I think that rethinking all of the things we assumed we know that might just not be right is one of the challenges we face as a community. The other big challenge we face is we're relatively small compared to the atmospheric science community or the computational fluid dynamics community, and yet the ocean is not a flat box with reentrant channels. It doesn't always look like the atmosphere. And so I think one of the challenges we face is that a lot of the work going on trying to push the envelope in terms of numerics often puts off the question of addressing the particular challenges of the ocean, irregular boundaries and significant variability, incropping and outcropping of density surfaces, the very long timescales of water mass conservation compared with the Eddy timescales. And so we are a unique community that's relatively small, but without perhaps sufficient attention to the particular challenges of modeling the ocean.
Steve, and then Graeme.
Steve Rintoul wrote a nice paper 6 years ago, I think, pointing to the importance of small things for the large-scale circulation in the Southern Ocean. And I think that that's an important thing we need to keep in mind when we're like the Gulf Stream problem and other big questions. often boil down to doing the proper numerics or parameterization, and that is what's in this room. So I wouldn't discount the work that we're doing here and saying we're not looking at the big questions, because I think when you go to those conferences and you talk about the big questions, it's very cloudy how you go about actually addressing those questions. And I don't mean cloudy because it's all cloud physics, but I mean, you know what I mean? It's hard to really grab onto something. And there's so many things we know we're not doing properly. And I guess there's a bit of faith that when we do the numerics and the physics right, we hope that that has payoff later. We've seen it in the past, and I think that that's a good indication that it might be in the future. So I want to give us more credit for doing the big questions in this room, even though often we're just looking at particular small questions, because everything that's, you know, it's, what is it? You know, every step counts to 1,000 miles. You got to take a step along that path.
Graeme? Yeah.
Yeah, thanks. Graeme MacGilchrist, University of St Andrews. I am obviously biased, but I do think that novel diagnostics can help us with persistent biases, looking at things in fresh ways. We're very used to just looking at SST patterns and tweaking something and see if it changed the SST pattern. So I think like the work that Liz, Maroon, and Tedra have been doing is a great partial approach in the North Atlantic of taking a new, and particularly process-oriented diagnostic approach could help us. And also the accessibility of that diagnostic analysis to people within the community. More eyes by more people on more processes will help to reduce some of these persistent biases.
Dan, are you there? Dan Amrine?
Yeah, thanks.
Go ahead.
I think we can make progress in thinking about modeling that's intended for purposes that ocean models are used for, and that's changed over the last 20 years. So we still don't have a workflow for communicating changes in the ocean down to community scales. I don't think we're incentivizing development necessarily that's centered on vulnerable populations. And I think the climate intervention and carbon dioxide removal is another big place where people are going to be leveraging these models. So I think we should be thinking about those new applications.
Okay, we are at 5 o'clock. And then we have an hour and a half of meeting after this one for some of us. So we should we should stop here. So thank you everybody again.